Okay. Well, good morning, everyone. Thanks for attending such day two. So we had a really great first day, and the purpose we're going to do this morning is we're just going to provide a very brief synthesis of the talks that we had yesterday, and then we're going to invite the leads for each of the breakout sessions to come up and give a very brief overview of the discussions that ensued for each question in the breakout sessions. So the day one summary is, really the first day was really to kind of set the stage for the air-sea coupling, the mechanisms for air-sea coupling, and how they affected both the ocean and the atmosphere in various different ways. And I just put down we gathered just a few key bullet points for the sessions that we thought were kind of common themes throughout the talks. And the first one was that I think is one of the more important ones, is that surface heat and momentum flux variability and their impacts on SST. So we saw some talks on how both surface heat and momentum fluxes have affected SST variability on short time scales and on longer seasonal time scales. We also saw that boundary layer parameterizations do not count in the ocean, especially do not capture all the fine scale turbulent motions in the presence of submesoscale variability. And this really affected the evolution of the submesoscale field in simulations. And we also saw quite a bit on how the impacts of the ocean states, on storm tracks, precipitation, and large-scale atmospheric circulation. And so this, we see that this air-sea coupling occurring on the mesoscales and the submesoscales are really a key feature for a number of climate processes on our planet. And we also heard a couple different takes on how exactly atmospheric fronts interact with ocean fronts. So, and this is a kind of a very interesting topic right now, partly because we still are just learning how ocean fronts are affecting storms and the storm tracks, but also it also raises challenges for how we look at air-sea coupling and data and models in the presence of this large-scale synoptic weather variability. So we can't necessarily say that weather is just a source of noise in our analyses. There's actually some sort of interaction where the ocean fronts are contributing to making synoptic weather variability. So surface currents are also emerging as a key process involving in the coupled ocean-atmosphere interactions. So they modulate the heat and momentum fluxes at the surface, and they also are a feedback mechanism for the ocean to the atmosphere. And so this is kind of emerging in the last 5 or 10 years as a very important process, along with other things. I should mention that sea state is also becoming an important variable. So as we go down to smaller and smaller spatial scales, these interactions between wind, waves, and currents are becoming a lot more important as well. And we'll hear a little bit more about that in the talks in the next 2 days. And while we were focusing on the mesoscales, so we all might kind of have our rough definition of what a mesoscale is, but usually kind of an operational definition is somewhere between 10 to 1,000 kilometers or 10 and 500 or something like that. But we're also seeing that as the models are, as our models' capability of being able to resolve mesoscale variability and start to simulate some mesoscale capabilities, and as we're also observing these finer length scales down past smaller than 10 kilometers, it's emerging that there's some really important processes that are important to understand also the mesoscale coupling that we're observing as well. So that's kind of just a quick summary of what we're kind of thinking about. And this sets the stage for our second day for today. And today we're going to focus a lot on the state of our observing and modeling capabilities for capturing mesoscale coupled processes and the kinds of things that we will learn as we keep resolving these coupled processes on these scales. So I'd like to ask all the breakout leads to come up, and we'll have a kind of a panel discussion, and we'll go through each of the questions here. So if all the breakout leads can come up, please. Your name is listed here. And it's meant to be kind of a little bit more of an informal summary of all the breakout discussions we had. So we will have the organizing committee will have all the notes from all the breakout discussions, and we will use those to synthesize our white paper discussions based on the community input that we have. So Stu, if you'd like to, so Stu did a very interesting, Stuart Bishop, he did a very interesting experiment, which he actually put all his notes into ChatGPT. And Stu, if you'd like to, so he cheated, but
did a surprisingly good job, I thought, for the people in our breakout. So this is the summary. I basically just took our
please turn on your mic.
put it in ChatGPT.
You can turn on your mic, please. Thank you.
And said summarize and put things in parentheses. And this was the output. Actually, I cheated. I did it three times. This was the third generation. So based on the notes, that our breakout session focused on improving estimates of surface fluxes on the ocean, sub-mesoscale and frontal scales, assessing the impact of mesoscale air-sea coupling on weather and climate prediction, and understanding ocean sub-mesoscale biogeochemical processes. That was kind of in some of the questions. Then promising observational approaches include sail drones, sounding arrays, drifting barges, autonomous systems, while modeling approaches include ensemble and sub-mesoscale permitting simulations, resolving synoptic and diabatic processes.
Stu, I'm sorry. You need to speak into the mic. We can't hear you in the back.
Variable grid size and vertical resolution exploration and coupled models. The community needs to improve communication, rank the top leading sources of errors, assess models, and concentrate efforts on specific regions. Opportunities exist to understand the carbon budget, biosensors on autonomous platforms, and ocean heat budget and chlorophyll feedback. I thought that did a pretty good job.
yeah.
Yeah, that was an interesting topic at the Gulfstream meeting last June.
Yeah. So that's really good. Hopefully that's not copyrighted. Okay, so we're also joined online by Helene Fun and Doug Vandermark. Are you both there?
I'm here, Larry.
Yeah, I'm here.
Okay, thank you very much. Okay, so the format we're going to do is we're going to go question by question. And if we could have just the group leaders, give us about a minute and a half or so summary, or even shorter if you think so. Doug, I'd like to start with you, if that's okay.
Yeah, sure, Larry. I'll do my best.
Okay, and we're going to...
we were able to get through all 4 questions. And so I will quickly try to give you a little breakdown. The first thing,
actually,
first question.
Doug?
Yeah.
Cool. Yeah, so we're going to do this question by question. So if you could address your comment for this question here.
Ah, okay.
Yeah, thank
Which
you.
one? The known uncertainties.
Yeah, so this question is, where are the known uncertainties associated with current methods to diagnose and represent submesoscale or mesoscale air-sea interaction in data and models?
Oh, man, I don't even think we did the same questions. That should be interesting.
Yeah. So we actually purposely scrambled the questions for each room so that we didn't get because what happens is people tend to focus on the first 2 questions and not the last 2. And so we wanted to get good answers for all of them. So if you did not do this, you can just say you didn't address it. We can move on.
We didn't address it. We can move on.
Okay. Thank you. Okay, Yalin, did you guys address this question? Oh, you're muted.
You mean the priority questions that the community need to address?
Yeah, or just your summary of the discussion associated with this question.
I didn't read the paragraph. We had a good discussion. I have a lot of questions that we think need to be addressed in order to better understand the influence of mesoscale air-sea coupling. And the first question we think it need to be addressed is we need to accurately represent the coupling process in order to understand their influence. So the first thing we talk about is the effect of wind-generated surface gravity waves, how to better represent their effect on the fluxes and boundary layer turbulence. And there are many parameterizations developed during the past 2 decades, for example, on Lamial turbulence that address the effect of surface gravity waves on ocean boundary layer turbulence. While those parameterizations are developed, they are not well evaluated in large-scale global models or climate models. And there's comparisons of those parameterizations. I did it myself more than 10 years ago, and recently Ting Li and Baylor Foxcapper also had this paper evaluate several of the parameterizations. And it turns out the discrepancies among those parameterizations are very large, much larger than the traditional schemes. And not only that, those parameterizations cannot give consistent improvement in the global models. While they can improve some places, they degrade the model performance significantly in other places, such as the Li et al. 2017 parameterization. They gave a very good improvement in the high latitude, mid latitude, but significant degradations in the equatorial region. So we think that a good approach for the community is to better evaluate those parameterizations and maybe combine their advantages and improving on their shortcomings to come out with like a unified parameterization that can benefit all modeling efforts. We also talk about the long-term climate models in contrast to the numerical weather or prediction models. They do not save their output at a high temporal resolutions. So this data cannot be used for analysis of high frequency phenomenon. However, if the data was saved at high frequency, they're probably too big to do. So we wonder if there's some ultimate good solution for this problem. We also talk about the consistency of fluxes in atmosphere and ocean models. So for many centers have coupled models now, but for many of them, the fluxes are calculated independently in both models. So the atmosphere calculate its own fluxes and ocean calculate its own fluxes, so it's not consistent. And also, when some models they does the consistent flux calculations, the different resolution of the models can also cause some inconsistency in the fluxes. For example, if the atmosphere grid is much coarser than ocean grid, it cannot resolve the final ocean structures that will influence the flux calculations. And also, how to address the fact of waves, surface gravity waves in the this flux calculations is not well quantified. So when the fluxes go to the ocean, they go past the waves, and the wave can keep some portion of it and give the rest of the momentum down to the ocean. And when waves break, they also give momentum to the ocean. So that process is not well addressed.
Okay, thanks, Helene. We have to move on to the next.
Sorry.
No, that's great. That was a really great summary. So actually, maybe ask our panelists to provide their comments as well.
Okay, yeah.
And, Sarah, would you like to start on yours?
Do you want to try and go through question by question?
That's what I was hoping.
Yeah, I'm sorry. The question that was before was the day 2 breakout 2 questions. Now we have a correct set of questions here. This is the question that we discussed yesterday.
Thank you.
And we want to discuss. It meant to be one question, 6 groups, 1 minute, 2 minute sort of high level summary per group. And
so, Doug, did you go through the first question? This one?
I guess we went through 4 questions. They're the ones that I see on the screen right now. So I can talk to any one of those when you want.
Okay. Why don't you go ahead and start on the first question then?
Okay, the promising one?
Sorry.
Okay, sure. We'll wait it here. Okay, for the promising observational modeling approaches, I think we had consensus that two-way coupled modeling seemed to be something that we spent a lot of time talking about as being a promising thing with a lot of the caveats that were just mentioned. So I won't maybe go through those. I've captured these in a document I sent to Sam. One of the questions that we asked about coupled modeling was, should the focus there be on weather prediction or seasonal climate scales? And the group seemed to think that the approach should probably, the focus should be on weather to try to properly capture some of these shorter scale processes correctly. Seemed like weather emphasis would be a better focus there. There was somebody that also mentioned a defunct, what they call S2S modeling program, which I didn't know the acronym, but there was a question about the status of that program. For promising observations, we just came through with, an interest in that UAV drone, as well as shipboard vessel opportunity LiDAR that seemed to be coming online to provide profiles of temperature and humidity where the satellite are only getting down to 850 millibars. That's it for question 1.
Excellent. Thank you. Sorry.
I guess one of the things that was really striking in this is that we had 3 people who were taking notes, and I looked at all last night and realized that we were clearly in the same session, but we had highlighted different things in our notes. So I recognize that anything I say is going to be biased by my own filter and what I happen to extract from notes when I went through all these things last night. But I think our discussion had a lot of focus on small scales and the role of small scale processes, really trying to find space to pinpoint the role of small scale processes in driving larger scale phenomena, both in coupled and uncoupled simulations. We asked questions about what scales matter, where are the transitions from small scale to large scale, how do we separate 2-dimensional and 3-dimensional regimes, what scales do you need to resolve to do that, and what are the priorities for scales that should be resolved, what resolutions do we actually need, what's desirable and what's essential. So I can stop there, but we obviously talked for a long time.
Thank you very much. Benjamin?
Right. In our case, we discuss the development on orbital tools to study vertical and horizontal exchange of the RC interface. And of course, we still need to resolve problems at high wind conditions and the horizontal and temporal resolution that need to be improved. And more on the observations, the group proposed that we should leverage on existing capabilities provided by gliders, sail drones, cargo floats, apex floats that provide also velocity measurements to expand the local measurements and explore spatial and temporal variability. And regarding the modeling approaches that are promising, it includes the development of physical parameterizations using machine learning applied to satellite observations, improving the representation of the impact to submesoscale to mesoscale process on the larger scale by analyzing model data from much higher resolution, and developing stochastical models based on, as well on higher resolution atmosphere ocean coupled models to better characterize prediction of uncertainties related to submesoscale, and of course advising coupled data simulation to improve the ocean initial state. And I think that few groups or nobody is assimilating currents actually, and probably something that we need to reinforce given the findings in other groups, how important the surface currents can be.
Excellent points. Thank you both. Next.
Yeah, so I might just add what hasn't been said. So I think there was an emphasis on like coordinate observation campaigns that are able to constrain the whole system better by combining different approaches. For example, there seems to be the ability now to have 2D observations of the ocean surface from a research vessel, and that combined with other autonomous observations seem to be valuable. Then, of course, we mentioned high-resolution global coupled models. They're exciting. They show a lot of interesting things. Then the need for better or better accessible cloud repositories to actually use the large data that's now available. That comes up also in the later points again. And yeah, then there was also mentioned variable resolution atmospheric models that are, I think, increase efficiency, and then so we can focus on specific regions, on specific processes. And then it was also mentioned, but not really discussed, high resolution regional models that are very good for doing process studies, for understanding small scale processes better, and the rise of machine learning in the field in general.
The rise of machine learning. Great. Okay, Stuart.
Okay, to add on to what's been discussed, we spent some time talking about observations and modeling, and on the observation side, sail drones are really providing some great coverage for capturing sharp fronts. And so it was brought up that some of the measuring sensors have challenges, however, such as the air temperature, which needs to be improved for sensible heat flux measurements. Some of our focus was on the atmospheric boundary layer. So we were discussing how sounding arrays would be a great improvement, so we can get it, sort of things like the atmospheric vorticity. The drifting barge was brought up, and then there was some discussion about maintaining long-term measurements is challenging in strong currents, that we don't have really anything like the Croatia Extension Observatory in the Gulf Stream region. On the modeling side, we discussed an ensemble approach, maybe something that it shows promise that sort of gets around some of the other challenges. We talked about submesoscale permitting simulations at maybe 1/48th. We had some discussion on the need to resolve the synoptic scale and what really is needed to resolve that. Reese brought up that at a 1/4 degree, there really is kind of a big breakthrough in the atmosphere from going from 1 degree to 1/4 degree. However, maybe we need to go higher. Some promise was discussed on the diabatic processes, so we need to focus on convection resolving models, realistic convection parameterization. We also had some discussion on what should the vertical grid be for the ocean and the atmosphere. Maybe there should be some vertical grid exploration. And I got a bunch of other things here. What is showing promise too is we need to have more of a community effort to collaborate and communicate to ensure consistency and standardization. And I think that's about it.
Great, thank you. Yeah, so it was all very wonderful. So we'll go to the next question here. And so the next question that we asked is, what are the top priority questions that the community needs to address to improve our understanding of the influence of mesoscale air-sea coupling on weather and climate prediction? And maybe Doug, we could start with you.
Sure. I think one thing to mention in our group, I don't think we really had a strong modeling component. And so some of our answers are coming more from the observational side. And the question that came up amongst the group was the very basic one of how to improve surface layer flux parameterizations. And the basic group input there was that a lot of these field measurements that are coming out recently suggest that we need more direct, just not bulk or scalar flux measurements with appropriate surface forcing, and these kind of strongly coupled conditions in order to better assess the bulk flux or the boundary layer flux parameterization accuracy and deficiencies. A related question was, do we need more accurate or new approaches for direct flux measurements for example, different platforms were discussed. As well as along that lines of sail drone, are there core measurements that platforms like that could or should be making to support that question? And a second and related question was kind of what link scales are important to resolve in surface flux observations and modeling. And there, I think it gets to the point that was just made about like convective regimes. And we were talking about the gray zone that sits between the parameterization and the quarter degree models and what LES is showing, and whether work needed to be done there now that we're pushing this high resolution ocean air coupling to these scales of 500 meters to 10 kilometers. And hopefully that captures roughly what we discussed.
Wonderful, thank you. Yellen?
I apologize. Before I actually went through question 2 instead of question 1. Do you want me to go through question 1 now, or finish the rest of the question 2 that we've been discussing?
Let's just go with question 2. So if you've already addressed it, then we could just move on to the panel up here and then keep going. If that's okay with you.
Okay, I'll add a couple things that we also discussed. We also discussed the fluxes, the calculations of skin temperature in the ocean versus the model calculated SST that is actually the averaged top layer temperature, which is inconsistent with what the flux calculation requirements. And we also talked the multi-scale interactions on how to link the local impact of large-scale features that is sensitive to global warming, and also how to improve the representation of bubbles, sea spray, aerosols for air-sea exchange, and how to accurately measure the vertical velocity and modeling them, including vertical transport, baroclinic instability, upfilling, and etc.
Wonderful, thank you.
So in terms of top priority questions, a lot of our discussion focused around questions about how you represent eddies and whether eddies can be thought of as stochastic processes, whether they should not be thought of as stochastic, how to deal with what might be rectified nonlinear effects versus random processes that come from small scales. And a similar range of questions appeared for diffusivity and how you represent vertical transfer in the ocean. Can it be thought of as a diffusivity or as something else? And then that led to further questions about Reynolds averaging. And so I think that was sort of, those were some of the core ideas that came out, and I'll let other people talk.
Thank you.
All right. In our group, we focus the discussion more on questions related to knowing how reliable the technology and the methods that are available are useful to evaluate Earth's interaction that we know. For instance, we know that most of what we learn from Earth's interaction comes from satellite studies. So one question is, how accurate are those measurements, in particular in extreme weather, where we know that there are serious limitations in the measurements. Also, another question was related to satellite products. How do we improve the accuracy of these measurements, in particular the heat and moisture fluxes? A comment was made that the poor quality of measurements of temperature and humidity are a major gap, where one main technical challenge involves a trade-off between resolution in the atmospheric boundary layer and versus estimates at the interface. So it's an issue that needs to be addressed. Also, how do we leverage current emerging technology to obtain more accurate measurements of collocated data, which is critical for weather in particular, severe storms? The time scales are faster, so faster than the ones that can be resolved with satellites. And it's very difficult to obtain measurements also in those extreme environments, so that's challenging. How do we develop a standard for evaluation and verification of new measurements? How do we make better use of observations to inform and guide model development? And one concern was also how to deal with the community access to large volume of data from numerical simulations that sometimes are not available to everybody, and also, of course, from other satellite products.
Yeah, I think we were a heavy modeling group. So what comes here is representative of that. So we should more look where models diverge to identify errors in models that way. And then there was also the need for having more accessibility to model data and observations again. And then there was a lot of discussion about what actually should be observed to constrain the models in a proper way, especially on small scales. And then we also had the notion of what are actually the metrics to compare these if you have these very intermittent, high fluctuating phenomena. Yeah, and then in terms of what are the top priorities, I think there was a good idea of actually looking more at the economic output and more actually assessing what the result of this new campaign or model run would be, and somehow find a way to weight these different approaches, because we have limited resources and we should figure out what we should prioritize on. So we would like to see more studies that actually quantify what the impact of a high resolution global model would be, and impact of a satellite would be. Yes, and then there was the idea of maybe focusing more of constraining statistics of extreme events on various timescales.
Okay, for our questions, we discussed how can we rank the top leading sources of error, which would help organize the community in terms of proposals and funding. Along that same line, we discussed what are the leading sources of sensitivities. Is it, for example, parameterization of clouds, fluxes, sensitivity to downstream and upstream. We also discussed what is the impact of sea ice on air-sea interaction, waves, and marginal sea ice zones. And where should we concentrate our effort? Should it be a specific region that we can generalize to more global? And I think that sort of rounds out our questions.
Yeah, this is some really great feedback so far. So thank you again. So we'll move on to our third question. What can be done to improve estimates of surface fluxes on the ocean, mesoscale or submesoscale and frontal scales, including their accuracy and representation of critical spatial and temporal scales? Doug, would you like to start?
Sure. I think our group picked out the sub there, so most of this is going to be higher resolution, I think. The group said that an approach would be needed to resolve the smaller spatial scales with observation and being able to isolate and understand how the fluxes vary and improve the accuracy of the spatial variability of the flux estimations, I guess. An approach there, one approach suggested was a field campaign focused on those really short scales. There was a mention of a more in-depth look at high-rate sail drone wind data, for example, to look at gustiness at these short scales. There was mention, I guess, of a solution that's already out there of 2 satellites that have been proposed for Earth Ventures, one looking at 3 to 5 kilometer winds and currents and another at 15 kilometer heat fluxes. And then we asked the question, I guess, of could more be done? And I think this fits with what we just heard from the last question with existing satellite data. Particularly, we talked about PBL height as being something that might be pushed in this context, as well as low-level cloud transition data. And then we were discussing several times about that idea of the preconditioning discussed yesterday with the hydrological cycle and the strong moisture flux ahead of the storms, and maybe improving satellite measurements of just assessing the accuracy of what exists right now in moisture fluxes could be something that could be useful. So that's our summary.
Thank you. Helene?
So we talked about more the disadvantage of more observations and the advantage of US ways and UAVs. I think Chris is a much better person to communicate this than I am. So Chris, are you there? Can you give the summary on this?
Or this is the third one?
Yes.
Third one there, right? Second one here. So yeah, we talked about observations from various platforms that would get at these, rather than point measurements, get at these larger submesoscales to improve the processes at the submesoscales that would impact mesoscales. So using surface uncrewed surface vessels or vehicles like sail drones and wave gliders, UAVs, all these get some reasonably uncontaminated measurements. Moored observations, I think Jim Edson has shown that using moored surface observations do a really good job of capturing the fluxes. And I'm not sure about this last one, improving surface forcing in river plumaries. That was another topic we had discussed. I think that was the main thing that we covered, correct, Galen?
Yes.
Okay.
Great. Thank you both.
So this was a question where our group also talked a lot about observations with the view that improvements in flux parameterizations will require direct flux measurements, possibly from an array of autonomous vehicles, possibly from a well-defined or well-designed moored observing system, and with satellite observations as well. We also talked a little about the possibility of a model intercomparison project, specifically targeting mesoscale processes. That's probably enough for now.
Thank you.
All right, so we also identify, of course, the need of having more collocated in situ observations, right? That's good for every purpose in this research. So also improve users' guidance on which estimates are better suited for different applications. This might require more organized efforts targeting cross-comparison of different products. Another point that we discussed was the need to collect more in situ fluxes to validate the satellite measurements and possibly combine in situ observations and satellites to better understand uncertainties. And of course, enhance the continuous measurements by expanding mooring buoy arrays and potentially allowing to assess spatial variability and temporal variability. And also another issue is probably use all the available data that it's available in the meteorological community. They have plenty of vertical profiles for atmospheric properties that probably can be used to evaluate satellite products.
Yeah, so we had the general notion that it would be very desirable to observe surface fluxes, but they will remain to be a noisy quantity. So it's actually a very hard job to do that. And instead, we would then fall back to more integrated metrics like mixed layer depth or SST. And that's how fluxes are. They prime bar terms, right? And then there was the notion to actually have more coordinate efforts between observation lists and modelers, especially for these small scales, for the submesoscale, since coordinated, like bigger campaigns are now actually better in constraining the RC interaction. We then can ask them to do it in a way that we compare to models in a better way. So actually sampling, going to this more from a sampling perspective, how to sample the upper ocean or like a specific domain properly so that we then can represent that in a model rather than focusing on features that much. Then two more points, I guess. Yeah, observations will, even though never be able to close the budget. So we probably throw out important terms in SC interactions that we can analyze in models if we're able to model that. And there's a potential segue to guide the community, which is actually the missing process in SC interaction, because we always rely on bulk flux formulas that have specific assumptions made in them. Yeah, I think I stopped there.
Okay, this was the first question our group focused on, and I think we discussed the need for higher resolution temporal and spatial scales for reanalysis products. We're typically at the daily time scales and quarter degree. However, it was brought up that these flux products just assimilate reanalysis and that we need a baseline for flux products. And coming with that, we need simultaneous measurements to estimate the fluxes accurately. Oftentimes, we don't have simultaneous sea surface temperature and air temperature. There are things like Sojourn that can help in validating, and that we need a baseline for the flux products in order to compare our observations and models together. So we need some sort of standard comparison. And that's about where we stopped.
Great, thank you. I'm hearing a recurring theme that we need a lot more combinations or co-located measurements of a lot more variables. So this is a theme that seems to be coming up more and more. So we have about 6 more minutes left, and we have 6 panelists and 1 last question. So each of you have about a minute to address this. The last question was, what opportunities exist to improve understanding of ocean mesoscale and submesoscale biogeochemical processes? And Doug?
All right. We had basically, I think, one idea was more Argo biogeochemical floats. And then, and I just bringing up that TPAS was looking at opportunities to work on this opportunity, I guess, already. They've been discussing it. And the second point that our group kind of knocked around as an interesting idea would be to have a repeat track research ship in a region where you have this kind of mesoscale air-sea interaction, and have that ship also be sampling biochemistry. Maybe such a repeat track already exists somewhere, or maybe one could be kind of proposed. So those were our big ideas there. Other than everyone's always interested in what the biochemical impacts would be.
Yeah, great, thank you. Helene?
Excuse me. We talked about the models getting better now at resolving the frontal features that can help to capture the biogeochemical processes such as the algae blooms. We also talked about improving our understanding of biogeochemical processes is critical, and the new pushes towards through the projects calls focusing on marine carbon dioxide removal or the monitoring, reporting, vertification, the MRVs, good pushes towards is a good opportunities for improving our understanding of the biogeochemical processes.
Wonderful, thank you.
So our group tackled this question first, which is how we knew the questions had been scrambled. And a lot of our discussion focused on really thinking there's new data being collected. What are the opportunities to capitalize on that? So we noted that there is biogeochemical data coming out of moorings, in particular WHOI. The satellite PACE is about to launch and will have offered new opportunities, and biogeochemical Argo is expanding the array, and so there's data coming from that, and as well as S-mode, where there is a biogeochemical effort coming from some of the observing that's happening as part of that. So it seems like if data are going to be available, there's a real opportunity to ask how to use them. We asked, what can we learn about vertical velocity by looking at biogeochemical processes? And we asked, should future modeling efforts prioritize biogeochemistry as part of the modeling?
Thank you.
All right. I think our comments were similar to Sarah's comments. So basically, in addition to the Argo float equipped with the biochemical sensors. We notice also that the apex plots can also be used for that purpose because they provide higher vertical resolution, higher temporal resolution, and currents as well. And another idea was also to equip the current observational platforms with these sensors, like moorings, right? And also was noticed the importance of the vertical velocities in controlling much of these processes. So it was proposed that we should improve our estimates of vertical velocities from satellites. And yes, also obtaining collocated orbital information of chlorophyll and upper ocean variability from more satellite observations.
Yeah, our group was a little blank there, I guess. So there was one good comment about using more optical properties of the upper ocean to assess biochemistry. And then there was since we didn't know much to say there, there was a general notion that we lack general education in this as a community, at least as was sampled in this room. So people don't have this in the back of their head when they plan campaigns, when they do their studies. So that's why it's lacking there. And if people would, in general, know more about these processes, they would immediately include them in their science.
Okay, for this problem, we talked about the sail drone once again, and we thought that it would help us in understanding the carbon budget, such as dissolved and organic carbon. There's been several campaigns in recent years, such as NASA Export, that can be utilized, SOCHIC, maybe I'm pronouncing these wrong, and SOLC. Putting biosensors on autonomous platforms could be something that could be utilized, and the chlorophyll feedback on the upper ocean heat budget was something we discussed.
Wonderful. Well, I think that's it. So let's thank all our panelists for their efforts today. So this is a really great discussion, and really appreciate it. For right now, we're going to a break until 9:15, and then we'll reconvene and get to more great science. So thank you all.
Okay, I see Helene is online. So Justin, you can kick us off whenever you want.
Yeah, thank you, Sam. We're now moving into state of the modeling capabilities. And I'm very happy to introduce the first speaker, Dr. Helene Hewitt. Is currently leading CMIP and is talking remotely. And I think we can have the questions about her talk after the talk this time because of the time difference. So I'd like to pass it on to Helene. Thank you.
Okay, thank you, Justin. Thank you for inviting me. We just checked my slides in the breakout room, and now for some reason I can't share them. So
we'll share it for you, Helene, and give you remote access.
Yeah, that sounds good. Okay, so yeah, thank you very much for inviting me. So as Justin said, I am now chairing the CMIP panel. My background is in ocean modeling, sea ice modeling. I led the chapter on ocean and cryosphere and sea level in the last IPCC report with Baylor. So I hope that I'm somewhat qualified to talk about this. So first of all, I thought I'll update you about CMIP and then go on to talk about that in the context of higher resolution. So so if we move on to the next slides, can I move those on?
Helene, if you go up to the top of the screen, there should be a little picture of a computer that says request remote access, and then you'll be able to advance your slides. It says ask to control.
Nope, can't see that. I'll just tell you if that's all right.
Okay. Yeah, yeah.
Okay, so next slide.
Okay.
Okay, so CMIP has a long history, as many people would know. It's supported a lot of policy information for reports such as IPCC, and with projections of different scenarios and ensemble spread across the multimodal ensemble. So CMIP 6 was a huge endeavor. There were 24 intercomparison projects, including projects such as HiRes-MIP. It involved 26 countries, many institutions, models, experiments. A lot of data was generated, so almost 25 petabytes, and all that data is available on more than 30 ESGF data nodes. But as we've progressed from CMIP 3 to CMIP 5 to CMIP 6, we can see that the complexity of the models has increased significantly. So things like ocean biogeochemistry are now included in a lot of those models. Next slide. And, you know, the data is used in many ways. So here I just pulled out an example from our chapter in IPCC, where we were able to combine information from different intercomparison projects. So the scenario simulations from CMIP along with ISMIP, the ice sheet simulations, and together they can come together to give projections of future sea level. And so the CMIP data, for example, gives you a multimodal spread for each of the scenarios of future sea level. Next slide. So I think anybody who was at a modelling centre would appreciate that CMIP 6 was the hugest endeavour ever. There was a lot of burden on the modelling centres. So we did a survey to see how we should change things moving forwards. And really there was a lot of support for what had happened in CMIP 6, that people wanted to evolve it, but not have a big structural change. However, to perhaps reduce this timeline that IPCC appears to impose on CMIP, and you'll see our suggestion for this later. Again, you know, focusing more on climate impacts and adaptation relevant experiments, making things more operational, like the forcings for the experiments. But, you know, still kind of having this infrastructure, but making it more user-friendly, having greater data access to the global community. And, you know, on that point, as well as nurturing young scientists, we recognise that we need to open this up more to the global south. Next slide. So the questions this raises for CMIP 7 is how many simulations or models can be reused, how many or which model intercomparison projects and scenarios are needed, how many ensemble members from each model or from the multi-model itself might be needed. Perhaps really pertinent to this meeting is what we should do with high resolution simulations. We might ask, do we need all the modelling groups to do everything with their state-of-the-art model? Also interested in how we can optimise the data storage, the analysis and the access. And well, we've put an estimate on this, but you know, we would like to reduce the carbon footprint. I think most people wouldn't be surprised or would guess that there was a large carbon footprint, and it's very hard to estimate that exactly. But we would definitely like to look to be reducing this somewhat. Next slide. So we've, within CMIP, we have set up task teams to look at various aspects, how the data is accessed, cited, the citations, how it's requested. So that's the burden on the modelling centres of getting the right variables out on the right timeframes and so on. We're trying to improve, update and operationalise the forcings, which Paul Durack and Vishali Nayak are leading. We're doing some work to benchmark the models, document the models. I'm also looking at the design of the ensemble in a strategic way, led by Ben Sanderson and Isla Simpson. And that will address a whole number of questions, but also including like which, you know, how many models are really needed to produce the information that's required. So next slide. So the model we're looking at, or the experiment design or structure, maybe to try and decouple CMIP from the IPCC timescales in its entire, too much, for not have everything pressurized by the IPCC timescales, is to define not just the deck, which is like this entry card to CMIP, the standards, some very standard runs, but to define a set of core experiments, which could include, for example, the historical, some scenario experiments, other experiments which might be needed, particularly for the 7th assessment report, assuming it goes ahead, and to have those delivering on that IPCC timescale, and then have these community MIPs being much freer to operate on longer timescales and not feel as constrained. So that's the idea, and we're very open to feedback on that. Next slide. So we really, even in this phase that we're in now, where CMIP 7 hasn't really been initialized, we're still kind of looking to support continuous activity. We might call this, we sometimes refer to this as CMIP 6+. So it allows people to use the infrastructure that existed in CMIP 6 or does exist to have new and ongoing activities. And so, for example, we had COVID MIP. And we can support the evolution of CMIP in this way. Next slide. Okay, so then the timeline. We have an estimate of when the IPCC timescale will be, and we have a fuzzy box around when that timeline is, because it might vary somewhat. So from that, we can work out when the earliest IPCC data deadline is and when the simulations might need to start. And so that would mean that the earliest simulations could need to start sort of mid to end of 2024, which is looking very close now. So there's a lot to do in a short timescale from a CMIP perspective. This includes identifying the MIPs, setting up the data request, having all the forcing ready. So we have a lot to work on. Next slide. So in CMIP, we're looking for wider engagement and feedback from the community, as I'm doing now. We have surveys out, we're doing workshops, drop-in sessions, things like EGU and maybe at AGU as well. We'll have town halls also at the Kigali meeting that WCRP are leading on. And we're really offering people through this direct interaction with the task team co-leads, the task team members, the project office as well. Okay, so next slide. So that's where CMIP is, and then I come to the question about what about resolution. So I've kind of touched on this, that we're sort of thinking about where resolution fits in. Obviously, everybody knows that there are the three axes: complexity, ensembles, and resolution. And you might say that CMIP has largely been in the complexity and ensemble space, looking at the increased complexity of Earth system models, looking at the multi-model ensembles. But, I mean, many people are familiar with the plot from Minobi, and I'm sure you've talked yesterday about other work in this sort of area. It's without doubt that the resolution is important, particularly in these frontal regions. We know from the ocean itself that the current resolution of many of the CMIP models, around 1 degree, isn't sufficient to resolve the Rossby radius. And if you look at this bottom plot that was in a paper that myself and Baylor and Malcolm and others were co-authors of, you can see that while we might expect resolution to have increased as time's gone on and computing power has increased, actually for CMIP it hasn't. Most of the runs haven't really increased even into the mesoscale resolving regime, let alone getting close to sub-mesoscale. So it is a question that is good to talk about, I think. Do you want to move forward? So I think one approach that's really important, that's others have advocated a lot for. I've realised that the top plot is actually from Steve Griffiths' seminal paper in 2015. So apologies for missing that off the references. So I think model hierarchies are so important, having the same model at different resolutions. You can look at the impact of parameterizing. Well, in this case, it's the mesoscale eddies, but you could imagine as time goes on, we'll look at how much we need to parameterize the submesoscale. And so, you can see in the top plot from Steve Griffiths' paper, the importance, this goes from low to medium to high resolution. And you can see how the medium type resolution, where you might not parameterize eddies, has bigger drifts. If we look at things like the Gulf Stream position, you can see that as you increase resolution in the same model, you get much closer towards the observations. You can see in the plot on the right from a paper that Malcolm Roberts led on, how much more realistic the coupling is between the ocean and the atmosphere as you go to higher atmosphere and ocean resolutions. And then I just show this plot of the Southern Ocean, and you can see that, if you look at the CMIP type resolutions, which is labeled the coarsest, the ACC is, I don't know, for want of a better scientific word, a bit of a blur. And then you can see increasing resolution of the fronts and the currents as you go towards even towards the 2.5 kilometer resolution, which is being run in Germany at the moment. So next slide. And the power of these, learning these lessons from things like the ocean-only models means these lessons can then pull through into climate models. So this is from work that was in the Primavera project, which Malcolm led on. And you can look at the matrix in both atmosphere resolution and ocean resolution. And you can see that it's at the very highest resolutions. If you look at the change in precipitation, you're starting to see changes in precipitation over Europe, which are larger than the spread from any of the lower resolution ensembles. And the hypothesis being that this is related to the position of the Gulf Stream and the North Atlantic current, which is much better in the higher resolution models. And next slide. So, I mean, this is way beyond CMIP now, but of course, everybody knows that there's this whole push to the kilometric scale, that there's lots of efforts now to build on regional modelling, where the kilometric scale is being looked at to try and develop these models particularly for global atmosphere models, for atmosphere, but also, especially I think for oceans as well. It presents many challenges, both for the modelling and the data storage or exploration. As I said, many challenges for the ocean, also for the sea ice, lots of issues for the coupling. I mean, Sophia Morton, who did a PhD with Malcolm and I recently, she's got a paper which shows that you really need your coupling. When you're coupling the models to get the best result, you need the atmosphere and the ocean to be at the same resolution. So that is quite a big ask at K scale. In the Met Office, Kath Senior is leading a science team on this, which includes K scale. And as many people know, WCRP, and there's other international efforts which are trying to move to K scale. Next slide. And this is just an example of what we're doing in the Met Office. So there's some work going on to couple a regional K-scale atmosphere model to an ocean model, which is at this kilometer, 1.5 kilometer scale. And when you compare with the atmosphere, you can see that there's some improvements. It reduces the drift. There's a cold bias that develops and stronger surface winds in corresponding to the cooler SSTs in the couple model, and perhaps linked to to more upwelling. So the idea is to expand this further into more towards the global scale. Next slide. And so really in summary, and hopefully this leaves time now for some discussion, it's very clear that CMIP and the whole coupled modelling activity has rapidly expanded in terms of the number of models and the complexity. But it's also absolutely clear that the increases in resolution haven't progressed as fast as we might have expected 20 years ago. So I often tell this anecdote that I started work at the Met Office Hadley Centre at the time when ourselves and NCAR were just moving to about 1 degree because Jem McWilliams had been developed and implemented, and it meant that we could run those without flux correction. And if you'd asked me 20 years ago, will we still be running 1 degree models, I'd have said no way, but that here we are. And so, I'm sure everybody here appreciates how resolution's needed by both the atmosphere and the ocean to capture these interactions at the mesoscale. I think it's computing costs really which have for the higher resolution, which has limited our ability to assess the importance of the resolution, because even in efforts like high-res MIP, we're generally not able to do very long deck runs, for example, long spin-ups and many scenarios. So I think the IHESP effort is important in that it's allowed longer simulations. And so a question maybe is what people's thoughts are. Should CMIP 7 be supporting or encouraging more higher resolution models? Does that have implications for the control runs in the deck? Should CMIP or other projects be interfacing together to build some more synergy? So yeah, very happy to have your questions.
Thank you, Helene, for the very nice talk and nice overview of CMIP. Welcome people to ask questions now, as I say, because of the time difference. While people are thinking about questions, if you want to ask a question, please come to the microphone if you're in situ. Benjamin.
Yes, great talk. I have a question. I remember one of my colleagues did a comparative study analyzing the impact of higher resolution in the vertical and the vertical mixing schemes in the numerical models, and also modeling initialization. And he found that probably the leading order problem to improve the air-sea interaction was, at least in the case of tropical cyclones, was to have the correct modeling initialization, meaning having the ocean fronts, the ocean features in the right place, because actually what is the position of those features in relation to the wind forcing is going to actually determine the actual fluxes and sea surface cooling and so on. So I wonder if you have a method to evaluate the modeling initialization in all these efforts that you are conducting.
Well, I would say I'd say in CMIP, that's really in the scope of the analysis teams. I mean, it would be, I think that is a really important topic, how well we've captured some of these frontal features. Are they in the right positions? Yeah, it's a really tricky problem because are you better to have that feature slightly offset than not have the feature at all? Yeah, sorry, I don't have all the answers on that, but I think it would be a really good thing for to be progressed further.
Just a brief reminder. So that question was from Benjamin Jaimes de la Cruz. And please remember to introduce yourselves when you're asking questions, because Helene only sees a tiny little picture of you.
Okay. Hi, Helene. So this is Sid from UMass Dartmouth, a PhD student. So my question will be very basic. So like the talk that you gave was more about like focusing, like one of the efforts is to like focus your efforts into going more into an higher resolution spatially, but I didn't get a chance of like understanding what time scales are you trying to resolve? Like what is the time resolution of the CMIP models? And do you think if there are like any efforts going on to improve increase the time resolution to maybe better future predictions. I'm not sure if that is one.
Yeah,
that
okay.
you are considering.
Yeah. I mean, what I would say is, so CMIP as it stands, I mean, it's not, CMIP takes the models it's given, so we can interface with the higher resolution efforts. And in CMIP 6, there was a model into comparison project called High-Res MIP. And so that was kind of the insight there into the high resolution. So it's not, we can't absolutely tell people what the resolution is. We take what we're given from the community. So sorry, what I should have said in CMIP, and thank you for that, because I will now revise this talk for next time I talk to people. So generally in CMIP, we do long control runs, which are, hundreds of years. And from those, we will then run from the pre-industrial, say 1850, to the present day with the observed forcing, or as close as we can. And then there'll be scenarios out into the future, maybe, often to 2100, maybe beyond. But there's also an effort to do decadal projection or predictions, so more initialized forcing, so going out for the next 10 years or so. So there's a whole range of timescales. So the data that is generated by CMIP can be on a whole host of timescales. There can be monthly means, annual means, multi-year monthly means. There's also definitely a push to have more data at shorter timescales. So, maybe even like daily, because one of the other efforts is to use CMIP to force regional models such as Cordex, and so they need very high resolution at their boundaries. So this is why it's such getting the request for the data is so important, because modeling centers don't want to keep rerunning their data, so their models rather. They want to have one good shot at the right data. So we're trying to service a whole range of people through that. And of course, for the air-sea interaction, the very high resolution data could be really valuable.
Hi, Helene. This is Brody Pearson.
Hi, Brody.
Hi. You mentioned in your talk that one of the goals for CMIP 7 was reducing the carbon footprint of the project by about 50%. But that seems to run in contrast to the trend towards higher resolution models going into CMIP. So what approaches, or how do you aim to achieve that 50% reduction? Is it through that reduction in experiments or some other way?
Well, as I said, Brody, you won't be surprised to know we probably don't know exactly what the carbon footprint of CMIP 6 was. However, I think when we define these core experiments, I think we'll be looking to, have, not kind of make the burden too high on those. We might also, and this is not decided, so this is me just discussing options. There might be ways where we can encourage modeling centers to look at whether every modeling center needs to run every experiment. And whether people will feel whether centers will feel they need to do that, who knows? But, if we think we've got enough information from a reduced number of experiments, that's something we could look at. And that's what that strategic ensemble design team is going to try to do. So it's a big ask. Maybe also for the, with the community MIPS, that's something we'll be talking to the MIPS about as well. We can't enforce it, but we can encourage people to think about it. And, what we're trying to achieve by producing the data is, for the good of the climate in many ways. So, it's completely in line with that ambition.
Schneider from the University of Hawaii. I just wonder, in exploring this three-dimensional space between resolution, ensembles, and complexity, how the need to improve some of the models and remove some of the glaring biases that they include, for example, the Coltang problem, how that addressing this problem, how that's informing your choice and the selection of exploring this three-dimensional space, ensemble, complexity, and resolution.
Yeah, thanks, Nicholas. I mean, there are lots of biases. I mean, things which we some of them have been improved. For example, some of the issues that we saw in CMIP 6 have been improved by looking at processes in the models. Resolution might be the factor in some cases, not entirely. So I think really, that does go back then to the modeling centers to look at their models and look at which biases they are addressing, or even the model into comparison projects to look at that. So it's, I'm kind of seeing it improving those biases and what that implies for the choices on resolution and complexity as being really driven by the modeling centers and the bottom-up community.
Please turn on your mic at the table.
One online question. I'd like to just have one question now on the online question, if you don't mind waiting for the open. No, I don't think that's a good idea. A quick question from questioner here and a quick question from the online questioner, please. First.
Okay. Hi, thank you for the nice talk. My name is James Larson. I'm a graduate student at Colorado State University. It was nice to hear you bring up the IHES data set, which is something that I've been looking at, because for me, my perspective is that there was a really nice collaboration, international, and it was a shame to see that shut down. I was wondering if you could comment on what you've seen that works well when doing international modeling collaborations, especially in a potentially volatile political environment.
Hi, James. Yeah. Yeah, it'd be great to see some of the results as well. It is tricky, I think communication is really important. You've raising the profile across the different national groups. Yeah, so communication and profile would be my suggestion. But when I say communication, I just mean building those strong collaborations where you can talk together freely and progress things.
And I'd like the online questioner to ask a question. I'm sorry, I can't see who you are, so please introduce yourself.
It's Chris Roberts.
Oh, hi, Chris.
Hi, Helene. Thank you for your talk. So you mentioned in your talk that the DEC experiments are the entry card for CMIP, and then you also highlighted this value of the hierarchies. And obviously the highest resolutions are unaffordable in these DEC scenarios. So are there any existing thoughts on how to integrate cheaper experimental designs into the CMIP framework? So maybe, I don't know, like AMIP snapshots at warming levels or something, so you can still allow some of these kind of kilometer scale contributions that might help inform assessment of biases that are sensitive to resolution without, I mean, even high-res MIP still had a kind of, you have to do a spin up and a control, and that's still a really expensive scenario to run with something at the cutting edge.
Yeah. Yeah, I mean, I've worked with Malcolm and you and others on high-res MIP, and I certainly see the value of that, even though it wasn't able to do the full DEC experiments. I mean, one thing we've discussed is whether we might have a DEC Lite version to allow some of these higher resolution efforts. What I would say is that the modeling drop-ins that we held last month, some of the modeling centers were a bit more lukewarm about that, and that people might misuse the data. So I think we might just, I think it's a good idea, and I like the ideas that you're suggesting. For example, the AMIP snapshot. I think we just have to think about how we do that presentationally, whether it's actually labelled as the deck or whether it's a MIP on its own, which might be a slightly less ambiguous way of presenting it. But yeah, I think we're in the spirit of high-res MIP. I would say we're probably quite open to that, at least as a MIP activity. Does that help, Chris?
Yeah, I mean, I wasn't expecting an answer really. It's just the sort of
yeah.
the idea of the value of CMIP, and it has a lot of reach, and it means people can use the data. And if there's probably people running simulations that might be interesting and useful if they're traceable to a CMIP deck, but otherwise they're kind of unknown and don't get. And it might help inform some of these questions, because I think high-res MIP was used quite a lot in the
PCC,
in the report. Even if they're not exactly the same things on that sort of process level assessment.
Okay, thank you very much, everyone. Thank you, Helene. I'm sorry this went over time a little bit, but I think it's important to have the discussion then. And I'd like to introduce our next speaker, Abigail Bodner. She's going to talk about a data-driven approach for the submesoscale, and she's presenting virtually. So I hope you can connect through okay.
Work?
Yeah, that's looking good. If you can do full screen.
Yeah. That work?
That looks great.
Great. Okay. Well, hi, everyone. I'm really sad not to be in Boulder in person. I was looking forward, but some personal stuff came up. But I'm still excited to share my work today, and I'd be happy for any follow-up questions. So this is work that's done in collaborations with the M-Square Alliance group, and Drew Bawada and Lorzana are of course essential parts of this. So I'm going to be talking about a data-driven approach for the submesoscale parameterization. And I know submesoscales have been discussed a lot, so I'm not going to get too much into the phenomenology, but I do want to highlight just the certain features that are important and relevant for the parameterizations that we've developed. So a submesoscale front is a sharp interface between two types of densities, and along these fronts, these instabilities form the mixed layer eddies, which are really the key part of the parameterization, the physics-based parameterization developed by Baylor a while ago. Here is a really nice video that we made recently of the surface buoyancy gradient given by the MIT GCM LLC 4320. So this is a simulation developed by NASA and ECHO that's at a resolution of 1/48 of a degree, so roughly 2 kilometers in horizontal scale. And the reason I think this is really cool is especially this motivates the core of the submesoscale parameterization, or the mixed layer eddy parameterization, which revolves around a relationship between vertical buoyancy fluxes and the horizontal gradient. So that was developed back in 2008 by Baylor et al., which came up with a relationship proportional to the buoyancy gradient times the mixed layer depth over the Coriolis parameter. And then in order to scale up from the smallest submesoscale front to the resolution of the climate model that gets used, there's this rescaling factor that gets introduced a few years later, where LF is the frontal width. And recently, oops, I didn't mean to play that again. Recently, we came up with a modification for this parameterization, where we explore the relationship between this frontal width parameter and boundary layer turbulence. So it's in a sense we're connecting between the submesoscale parameterization and the air sea fluxes, which is really a key part of the meeting today. So I'm not actually, unfortunately, going to be talking about this work specifically. It just come out a couple months ago in JPO, and a few of the co-authors are in person. So Leah Johnson, Baylor, and Peter Sullivan, I've seen them online as well. And I'm sure they'd be happy to chat about this. But I'm going to be using this work as motivation to explore a data-driven approach that's relating submesoscale buoyancy fluxes to variables that we think help set it. So as part of that is also going to be the dependency that we recently found between the submesoscale parameterizations and these surface fluxes. So this is actually the data set that we're using for a data-driven method. So we've sampled the MIT GCM LLC in these different regions around the world. And the buoyancy gradients really highlight the different variability of these type of features around the world. And you can see that some of our regions really encompass a lot of this active horizontal gradients, and these tend to be also very active submesoscale regions. A lot of them correspond to observational campaigns that took place, and whereas others are also in kind of out in the middle of nowhere in terms of submesoscale activities. And this is really an important part that we want to capture, because we want to make sure that our data-driven method is capturing both places where we think of submesoscales as being active, but also can generalize to other places as well. And there's a combination of different timescales going on here, and some of that's related probably to the wave activity in the simulation, and others are related to air-sea coupling, or at least the response of the simulation to the atmospheric forcing. So just to recap, we have a super high resolution simulation, 1/48 of a degree, and we're sampling these 10 by 10 degree regions from the global simulation. This simulation is really massive. It's petabytes of data, and there's a total of 14 months available of hourly data. We try to remove some of this wave signal because we want to make sure it doesn't interfere with our buoyancy fluxes. So we average the variables over a 12-hour period, and then we have an additional 7-day moving average that comes in when we coarse grain. But we use this data set to compute the subgrid vertical fluxes directly from the data. And the reason that we're framing it in this way is we're trying to stay as close as possible to the current mixed layer eddy parameterization in terms of the stream function and how it's implemented currently in GCMs. So this stream function is a skew flux format, and we don't have to get into that too much, but the most important piece is that there's this dependence on the vertical buoyancy fluxes averaged over the mixed layer. In the physics-based approach, the Fox-Kemper et al. Parameterization, that term gets expanded out by a theoretical relationship, whereas here we are going to be using the vertical fluxes that are directly computed from the data and train a neural network to learn them. And I'll just mention that the vertical fluxes, the way we're defining them, it's a little bit different than the cloud-based submesoscale framework that Takaya led a few years last year. But we are using a coarse graining. So sorry, we have the super high resolution data that we're trying to bring to a resolution of the kind of standard GCMs. So for that, we introduce a coarse graining operator as well as the depth averaging to stay pretty close to how the current parameterization is framed. And a couple of weeks ago, I gave a talk at the CSM workshop, and there were a few questions that I thought were really excellent to ask. How good is this data, and how can we trust it really for training this type of submesoscale parameterization? So on this left panel over here, this is the variance preserving WB cross spectrum. So really this is showing correlation between the vertical velocity and the buoyancy over depth and wave numbers. And this is in one of the regions near the Gulf Stream. And the main takeaway here is that you can see that the peak of this cross spectrum is located in the smaller scales, so on scales that are roughly 10 to 15 kilometers. And furthermore, this peak is located within the average mixed layer depth in this region. So what this is saying is that first order, these vertical fluxes are really coming from the smaller submesoscales. And if we average over that depth, so this is again what's coming into the current parameterization in GCMs, is we can look at how this varies across these different regions. And we can see that there's quite a lot of variability also in terms of the locations, and I'm sure there's also a lot of seasonality in here. But the results I'm going to be showing today are restricting to the regions where we see the peak in the cross spectrum in these smaller scales. And one of the next steps that we're going to be doing is to understand how our method also generalizes to these other locations where we might see a more complex relationship with WB. So the slide is a little dense, but what the highlight here is that this is how we're framing the parameterization. So we know from the Fox-Kemper parameterization and also from the recent modification that we made that there is a relationship between WB and other variables that the GCM resolves. And we're using these as inspiration for the input variables that we're going to be training our neural network for. So in particular, we're computing directly from the data, the mixed layer depth, boundary layer depth, surface wind stress, surface heat flux, Coriolis parameter, average buoyancy gradient, and the average stratification. And in all of these different variables, we are mimicking the way the GCM would solve these. So we coarse grain the resolution to a 1/4 degree. And we have on one side the inputs of the variables of these different sets of variables that the GCM can resolve. And on the output, so the target that we're trying to predict is going to be the depth average vertical fluxes. And in a sense, this is exactly the same way as kind of the physics-based or standard parameterizations work in models, where we've got a relationship between the quantity that we want to resolve, but we're not able to in the model, and other variables that we are able to resolve. But rather than a theoretical relationship between the two, we now replace that with a convolutional neural network, which is essentially learning more complex relationships between these vertical fluxes and the variables that help set it in the model. So this is the current framework, and we trained this network. So a lot of the work actually was trying to get the data, which was quite a task, and also pre-processing it and getting it kind of ready for this framework that in a way that makes sense. So I'm just going to show some results from one of the examples, and this is still a work in progress, and there's a lot of sensitivity that we're testing to it. But from the different regions, we've extracted 8,000 samples, and this is given only from those regions that I showed where the peak of the co-spectrum is given in the smaller submesoscale range. We shuffle all these samples around, so time does not become any more a factor, and we retain 90% of the data we use to train the neural network, whereas 10% of it the network never sees, and we only use it for testing. So here's just a visualization of what some of the results look like. So on the top left here, this is the quote true data from the LLC data set. So this is the depth averaged W prime B prime, the total one. And to the right of that, this is the prediction by the CNN, so the neural network. And you can see that, you know, some of the larger features are being captured, and as well as these negative buoyancy fluxes that are given from the true data. Down below, we have the Fox-Kemper 2011 parameterization. So this has a rescaling factor that's proportional to the mixed layer depth deformation radius. Sorry, the mixed layer deformation radius. Whereas here is the Bodner 23 parameterization. So this has the rescaling factor that's proportional to boundary layer turbulence variables. And in both cases, you know, we see that we get these kind of larger scale features extracted, but by construction, the Fox-Kemper parameterization is not able to get these negative values, and that's kind of the main difference over here. I'm going to sweep through a few other examples, but you'll get the gist of it. Different panels kind of give different results. And if we looked across, you know, all these different samples of the testing, here's a PDF, so some statistics to give us a better understanding of what this really means. So if we compare the Fox-Kemper 2011 parameterization versus quote the truth, which is the data from the LLC, we get that it kind of overshoots in some cases. What I was, you know, excited to see is that our modification seems to do a better job in predicting the fluxes from the true data. So the relationship with boundary layer turbulence seems to be a really key part of being able to mimic what's really happening in the data. And then the CNN is really able to capture the statistical range that's closer to the true data. And of course, you know, you get these small negative values that are coming in, which by construction are not possible. So all these different parameterization versions do resemble in large scale statistics. The parameterization, the modification we just made recently does improve the predicted fluxes compared to the older version. And the neural network really tends to predict a larger range of examples that's closer to the true data, including these negative fluxes. One thing that's important to note is how important are these negative submesoscale fluxes? How sensitive is that to the analysis that we're doing? So this is something that I'd be very interested to explore, especially because that has a really important implication to the air-sea interactions and how the ocean's responding to atmospheric forcing. And then, you know, what's next? So going back to this framework, we've used these input variables that are inspired by the current formulations, but, you know, then there's the question of, do we really need all of these variables? Are they all super important to predict the fluxes, or maybe just a subset of them? Or rather, are there other relevant variables that we're not currently using, like strain and divergence, which have been shown to be important and relevant for submesoscale fluxes? So that's something that's still being tested right now, and I'd be happy to discuss later. So while I have the attention of everyone here, and I know some of you have already heard me talk about it, but I did want to advertise for Climate Match Academy. So this is an educational event that's happening this summer that I've co-founded with a bunch of other enthusiastic climate scientists. And I think that in particular, people that are in the CLIVAR crowd would really have a great relationship with Climate Match. So we're trying to teach computational tools for climate science. And we're using a virtual platform that was developed by NeuroMatch Academy, which was able to reach thousands of students worldwide, including the Global South. And we're extremely excited about this opportunity to teach climate science, and this is really the future generation of climate scientists. So if you'd like to get involved, there are a few of our content developers that are currently in the crowd, and I'm sure they would love to tell you about all the exciting work we're doing. And with that, I'll summarize my science talk. So we're developing a data-driven approach for parameterizing the vertical submesoscale fluxes given by the ultra-high resolution MIT GCM LLC 4320. And we've compared different versions of the current mixed layer eddy parameterization. So all of the parameterizations resemble in large scale statistics, and our recent modification to the mixed layer eddy parameterization does improve the fluxes compared with the older Fox-Camper 2011 parameterization. And the neural network really does an exceptional job of predicting the fluxes in a way that really resembles the true data. It also is able to capture these negative fluxes, which by construction was not possible by the other parameterization. And we're currently testing sensitivity to these input variables and developing different approaches for how to actually implement this in GCM. And that's a lot of the work that's going on right now in MSCR lines, which is very exciting. So yeah, with that, I'll stop and I'd be happy to answer any questions.
Thanks, Abby. So while we're getting organized for maybe a question or two, I just wanted to point out that a lot of cameras came out when you mentioned Climate Match. So hopefully you'll get some responses from this crew.
Oh, great. I'm so excited. Yeah.
Do the questions now or at the end?
Yeah, so Abby, do you mind holding on for a minute to hear through Jacob's talk, and then we'll have some questions at the end? We're trying to sequence the question timing. Thank you very much.
Yeah, sure.
I'd like to introduce our next and final speaker is Jacob Wenegrat from University of Maryland, talking about more than a length scale air-sea interaction at sub-mesoscale fronts.
Yeah, thanks. Nice to be here. And so I'll try to make the argument here today that although we often talk in this sort of setting about the submesoscale in terms of a length scale, it's really a dynamical regime. And that opens up, I think, the possibility of new mechanisms for air-sea interaction that we might consider. So, you know, we've heard things like this already in this, this meeting. Submesoscale sits between about 10 kilometers and 100 meters. At the small end, it becomes turbulence. At the large scale, we transition to the mesoscale. But from a dynamics perspective, we also often define the submesoscale in terms of the Rossby number and Richardson number of the flow, which is a more informative definition in many ways. So the submesoscale under this definition is those processes at which the Rossby number and Richardson number are order 1. And so, of course, that may fall in this particular length scale, but it also often can fall at, for instance, larger length scales. What that means is that planetary rotation and nonlinearity are, of course, important. Stratification is important, but these motions are much more fully three-dimensional than the large scale. That is, they're often associated with their own sort of internally generated, very strong vertical circulations, which is an important thing to think about. So how does this show up in air-sea interaction and coupling? We believe that many of the physical mechanisms we know from larger scales also transition down to these smaller scales. That includes the thermal feedback, the current feedback. We've heard examples of that, particularly yesterday. The thermal feedback in large eddy simulations, for example, seems to be quite strong at the submesoscale. So this is a snapshot from a large eddy simulation of the atmospheric boundary layer with flow along essentially a cold filament. So that's sort of indicated at the bottom there. And you see over the warm SST this anomalous convection. over the cold SST, this development of a stably stratified internal boundary layer. In these sort of simulations, this is associated with a really strong response in the wind. But I do want to highlight that I think it's an open question to what extent these sort of results from these super idealized setups really hold in the presence of realistic submesoscale turbulence. And a key aspect of that is that the atmosphere here is essentially always in a large Rossby number regime. That is, the length scale of the fronts is so small that it doesn't really matter what the orientation of the wind is relative to the fronts. The atmospheric Rossby number is always large, and that means that the dynamics of the boundary layer response will be nonlinear, and then advection will be important as well in the temperature or buoyancy budget. An alternate way that SST variability can enter this is actually directly through fluxes of eddy potential energy. So Lionel showed an example of that from work by Igor WHOI. He had a poster yesterday, and that's still online, or I'd be happy to talk with you about that if you didn't have a chance to see it. Now, the current feedback in contrast, so this is a definition. We've seen a bulk formulation of the stress using the surface relative wind speed. This is essentially entirely local, unlike that thermal feedback on the wind. And so that suggests that this would be robust, regardless of scale. And of course, then you can define this perturbation stress, tau prime, simply the difference between the full stress and that using the standard sort of Earth relative wind speed. And by definition, this, of course, introduces small scale variability in the surface stress. So here's an example from an idealized simulation. So SST at left, Rossby number in the center. So this is sort of order 1 Rossby number, dynamically submesoscale. And then at right is the zonal component of the perturbation stress normalized by the sort of background or mean zonal stress. And so some of these values are large. It's, here it's pretty moderate wind, about 7 meters a second. So you reach, 20, 30%. But more important, of course, is that there's this correlation between the wind stress variability and the surface currents. And so zooming in now on a particular cold core eddy here. So this is a cyclonic cold core submesoscale eddy. The zonal velocity is showed in the second column. And then by definition, there's this zonal perturbation stress, which is anti-correlated with the surface currents. And so this gives rise to this negative wind work eddy killing effect that has been well studied both at the mesoscale and seems to show up in models at the submesoscale as well. However, in the rightmost column, I'm showing now the meridional buoyancy gradient. So this is a cold core eddy. It's associated with a meridional buoyancy gradient that is positively correlated with the zonal portion of this current feedback induced stress perturbation. And what I'll argue is that this sort of correlation with the buoyancy gradient allows this air-sea coupling effect to affect the Ekman buoyancy flux at fronts. And this is really a key driver of submesoscale variability. So it's simply the dot product of the Ekman transport with the horizontal buoyancy gradient shown schematically at left. So in the case that the wind is aligned with the frontal jet, what we call downfront winds, this leads to a transport of dense water over light water, drives convective turbulence. And to put this in context, observations in western boundary currents, show that this can be equivalent to, an effective heat flux of order 10,000 watts per meter squared. So this is almost always a leading term, if not the leading term, in the buoyancy budget at submesoscale fronts, really outpacing air-sea interaction, direct air-sea heat fluxes. Perhaps more importantly, from a dynamics perspective, is that the Ekman buoyancy flux is directly associated with the flux of potential vorticity, and that matters a lot for the sorts of instabilities that arise at these ocean fronts. And just plugging in the definition of the full surface stress, it's pretty straightforward to see how this inclusion of the current feedback effect will directly modify the Ekman buoyancy flux as well. That is that rightmost term is the effect of the surface currents on the Ekman buoyancy flux. Now, this matters a lot potentially for submesoscale fronts because the Ekman buoyancy flux does two things. One, it can destroy or inject PV. So at right in the top is a snapshot. This is an initial value problem, but you see this strip of negative PV at this front, and this sort of condition in the ocean is often created by downfront winds, Ekman buoyancy fluxes that are destroying PV. And this can be unstable to these very fast-growing symmetric instability modes. So here, after 5 inertial periods, you see this banded structure in the middle panel with these overturning cells aligned along isopycnals as characteristic of SI. And the SI grows by extracting energy from the front. So it's extracting energy from the background thermal wind shear, and the rate of that energy extraction is also set by the Ekman buoyancy flux. So it not only creates the conditions for the instability, but it sets the rate of growth. These instabilities, though, are associated with a lot of shear and give rise to secondary Kelvin-Helmholtz instability. So this is a snapshot from a similar simulation where you see this banded structure here in vorticity rolling up into KH instabilities. And so really these instabilities serve to open this pathway. They're taking energy from the balance flow, and most of it is going directly to turbulent dissipation. And again, the rate of that is set by the Ekman buoyancy flux. Okay, so how significant is the current feedback modification? At left is a snapshot again from that channel simulation of the total Ekman buoyancy flux. It's posed here in units in terms of an effective heat flux for comparison. The middle column is the sort of background or Earth relative standard formulation, and the rightmost column is the contribution of the current feedback. And so the first thing I'll note is that this is largely of the sense to inject buoyancy and PV into the mix layer. That is, this effect acts to reduce the downfront component of winds, and so it acts as a source of PV to the mix layer. From a scaling perspective, we can sort of anticipate when this might be important. It depends on the strength of the surface currents, that's U naught, how strong the winds are, U sub A, and then importantly, the angle between the wind and surface thermal wind shear. So, winds can be aligned with fronts, but don't have to be. And so this scaling suggests several setups where this contribution may be important. The first is when you have strong surface currents relative to the wind, and that's the bottommost row here. So this is associated with this meander of this jet. It has strong surface currents of about 1 meter per second. You can see that the net Ekman buoyancy flux is still out of the ocean, that is destruction of PV, but here this current feedback effect reduces that destruction of PV by about 20%. The other setup when the scaling suggests this will be important is when the winds blow across a front, and that's shown in the upper row. So the winds here are oriented towards the northeast, blowing across this frontal feature, but there are these current feedback induced Ekman buoyancy flux of order several hundred watts per meter squared, equivalent heat flux here. And this dependence of the sort of standard formulation on the wind alignment with the front also suggests that in an integrated sense, these regions of very strong positive and negative Ekman buoyancy flux can integrate to a much smaller value. And indeed, we've seen that in realistic simulations, for instance, of the subtropical mode water in the North Atlantic. And we see that here as well. So in the top panel is the Ekman heat flux as a function of time. The blue line is that same simulation I just showed with the current feedback. The dashed orange line is a companion simulation, but run without the current effect on stress. So there's about a 50% reduction here in the mean Ekman buoyancy flux. So the particular values here, I'll just note, of the heat flux are really a function of the parameters I've chosen, so not necessarily general. But this reduction is expected to be sort of a general feature of including the current feedback effect. And that's directly reflected as well in the PV injection. So you see there's this rate of increase of PV in this simulation that is about a factor of 2 larger than when you don't include the current feedback. So this suggests the possibility that in some integrated sense, this might contribute to the PV budget. But even when fronts remain symmetrically unstable, that is, the net EBF is of the sign to destroy PV and give rise to these fast-growing instabilities, as we believe are common in things like western boundary currents at the edge of mesoscale eddies. This has a potential to change sort of the energetic pathways. And so this is a schematic of some of the energetic pathways that could be at play. And the right side of this is really probably the most familiar. That is, baroclinic mixed layer eddies are extracting available potential energy into eddy kinetic energy. And the best studied energetic aspect, I think, of the current feedback is the so-called eddy killing effect. That is, this perturbation wind work that acts essentially as a damping term in the kinetic energy equation. So it's this term in brackets times the surface kinetic energy that shows up on the right-hand side of the eddy kinetic energy. Symmetric instability, as I said, has this alternate energetic pathway. It's extracting energy from the fronts through the geostrophic shear production. That rate is set by the Ekman buoyancy flux and then cascading it largely to turbulence. And the change in the geostrophic shear production turns out to scale quite similarly to this eddy killing effect. So this coefficient is essentially the same as the eddy killing effect. The only difference here has to do with whether the surface currents, how that compares with the change in geostrophic velocity across the mix layer. So delta UG here is the change in geostrophic velocity. So essentially, which of these is sort of dominant in terms of the energetics at a submesoscale front may come down to how baroclinic or barotropic your surface currents are. So in summary, the submesoscale is really a dynamical regime. Thinking of it in that way, I think allows the possibility that there may be sort of new mechanisms of air-sea interaction that differ from those that we understand from the mesoscale. An example of that perhaps is this current feedback on the Ekman buoyancy flux, a source of PV and buoyancy to the mix layer, which is, has the possibility of modifying these geostrophic shear production terms, which directly cascade to turbulence in the boundary layer. And so, in the interest of perhaps sparking discussion, we do have many open challenges. Model resolution continues to be a huge challenge at these scales. We are unable to directly resolve these sorts of instabilities, even in our sort of submesoscale resolving simulations. Cross-scale effects, that is, the submesoscale is affected, not just directly by air-sea interaction, but also through changes to the larger scale. And it's quite difficult to disentangle that, even in these sorts of idealized settings. And finally, I'll just note that there's sort of shared parameter dependencies between many frontal processes, from mixed layer instability to the Ekman buoyancy flux to the sort of mixing-driven overturning circulations, all of which, for example, depend on the strength of the fronts. And that can change again through both direct and indirect changes. So I think we still have a lot of work to do to sort of disentangle this. So thank you.
Thank you, Jacob. And just before we hand over to General, I had a question. The definition of submesoscale used on an early slide, where the Rossby number, Richardson number was similar, is that, I don't know much about this subject. Is that generally accepted definition, or is this something you've learned from your experience?
Yeah, I think it is generally accepted by dynamicists. There's the definition of the submesoscale sort of changes depending on what's available to you. So for instance, you'll see papers written that say 50 kilometers and smaller is the submesoscale. But, and there's not necessarily anything wrong with that. But my point is just that, the submesoscale is dynamically unique. The circulations, for example, can be quite strong, internally generated. And we really ought to be thinking about how, these air-sea interaction effects play into that.
Thank you. Taylor, would you like to carry on the discussion? Or?
Oh, yeah. So, Abby, are you still here? And Helene looks like she's also still here. Yeah, so I don't know if Helene is still here or not. Well, we won't worry about that. So we're switching over to a panel session before we take a break. If anybody has any continuing lingering questions for any of our presenters, although I'm not sure that Helene is still, it's quite late there, so I'm not sure that she's still on. We could do that. Or if the presenters have questions for each other. But people should come up to the microphones. I think Yuri is here first, so go for it, Yuri.
Yuri from UMass Dartmouth. I have two quick questions. I think the first one is quick, actually. So the first one is to Abigail. And I would like to know a little bit more about how you define the boxes that you showed, and if you have thought about using unsupervised method to define the variety of groups that you're going to have, that you're going to need to model this.
Yeah, that's a great question. The way I've defined it so far is just by really selecting and cropping regions. I started by places that are kind of inspired by the paper by Hector Torres a couple of years ago, where he studied the energetics of submesoscales in different regions around the world. So that was kind of the first 8 regions I chose, and then I expanded further to other locations that have been relevant for submesoscales. But no, I haven't. Are you talking about like using GMM or something like that for classification?
Yeah, using some yeah, some grouping algorithm to define the different dynamical regions or something like that.
That's a really great idea. I have not gotten that far, but I would I have all the data. I mean, if that was something you'd be interested in, I'd be happy to discuss. Yeah, I think there's so much more that can be extracted from this data set than what we're currently using for training.
And my other question is to Jacob. You showed us your work with Thomas that shows the importance of symmetric instabilities in the on the forward cascade. And there are some recent works on the catalyzing effect of the inertial waves. And I was wondering, what do you expect to happen if you have at the same time the inertial waves, like internal waves and symmetric instability in a front?
Yes, so symmetric instability are essentially internal waves when the restoring forces become non-restoring in the negative PV regime. There has been some work, for instance, in the Gulf Stream, though, on the sort of addition of symmetrically unstable conditions with sheared inertial oscillations, and it essentially modulates the growth rate, but doesn't really change the picture.
Thank you.
Hi, Lionel Renaud from IRD, France. I have first two quick questions for Abigail. So the first one is on the parameterization you are developing. Did you apply any physical constraint, and you plan to develop a scale-aware parameterization with that?
Yeah, I haven't thought yet about a scale-aware parameterization because, I mean, there is the dependency on the grid scale and the current parameterization. And that is something that can easily be adjusted if I change the way I'm course graining, but I don't currently have a scale-aware piece in there. And what was the first question? Sorry.
It was whether you apply the physical constraint on your network.
Okay, so is this referring to the way other people have used like conservation laws in the network?
Yeah.
Yeah. So in this case,
whatever.
yeah. So because I'm not actually predicting the stream function or the flux divergence, that's not something that comes into play in the way we currently have, and we're predicting the actual fluxes. But that is something that we're considering if we change the way the implementation will go into GCMs. So a slide that I removed because it was too long, but we're currently exploring ways of, for instance, looking at a stream function, predicting the stream function directly, or predicting like a diffusivity-like framework. And that would be very important in those cases to make sure we're not adding more heat to the ocean and stuff like that. Yeah.
Thank you. And I have a quick question for Jacob. Did you see any large scale upscaling impact on the reduction of?
Yeah, in terms of the idealized simulation, yeah, so certainly, kinetic energy differs, vorticity, strain, like all the distributions are different. It is, difficult to figure out exactly which air-sea interaction mechanism gives rise to that. Yeah.
Thanks.
Hi, my name is Sikarai. I'm from University of Rochester, PhD student. My first question is for Abigail. You have done some coarse graining. I was wondering, when you do coarse graining, do you do such that the divergence, non-divergence, or the divergence is preserved as you are looking into submesoscales? I've often observed that when you have a non-divergent field and you coarse grain it, it suddenly becomes divergent, and that will create some residual effects, and it may contaminate your energy equations for the coarse-grained field. So have you seen into what that does to your coarse graining?
Yeah, that's a really, really good question. I'm currently interpolating everything onto the same grid. So I don't have a lot of the issues that if I were to keep it at, in a C gridded, like the edges and all that. So I've somewhat avoided that problem, but that's not necessarily a good answer. I'm also taking all gradients after the coarse graining in order to resemble what the GCM would do. So for instance, the buoyancy gradient is being computed on the coarse resolution data versus the high resolution. So we're preserving some of what, a GCM-like implementation will look like.
Yeah, my second question is again related with the coarse graining again. So when we coarse grain, if we coarse grain with density weighted coarse graining, then we'll find the energy equations different than when we do a regular coarse graining when it's not density weighted. Like the cascade terms becomes a Galilean variant when you do regular coarse graining, whereas when you do density weighted coarse graining, it becomes Galilean invariant, the cascade terms. So as you are parameterizing the subscale terms, do you see any differences when do you expect any differences to come when you apply density weighted coarse graining or like regular coarse graining?
Yeah, that's a really good question. I think that would be also increasingly important as you vary the locations around the world too. I mean, I don't know how much detail I should get into, but I'm using like the package, the ECMF package that's using the density weighted coarse grading. So I think I'm avoiding that, but I would be very happy to discuss this with you.
Thank you. And I have a question for Jacob. I was wondering, so this might be a very basic question. So the eddy killing term is not a cross-scale term, right? So it only appears if you write the budget equation for the energy. The eddy killing term does not appear in the mean equations, but it appears in the subscale equations. And it affects the subscale kinetic energy. And then that's how I perceive that the eddy killing will affect the cascade as it indirectly affects the cross-scale term by affecting the arrows in the Lorentz energy cycle, right? I was wondering how this Ekman buoyancy flux appear in the energy equations. Does it appear in the potential energy equation, kinetic energy equation, or does it appear in the vorticity equations?
Yeah, it appears as a shear production term, essentially. So you have a shear production term that involves the geostrophic shear, and that term scales as the Ekman buoyancy flux.
Oh, okay. Yeah, thank you. Thank you very much. Yeah.
Thanks, Shigar. I think Leah's next, and then Moma, then Brody.
Hi, Abby. This is Leah Johnson from APL. So I was really impressed by your PDF of the CNN and the MIT GCM. And I too was interested in the negative buoyancy flux there. And the other thing that can cause it, that same sign would be a down gradient flux from turbulent mixing. And so I was wondering if you know kind of how large the W prime B prime from the submesoscale compares to the turbulent buoyancy flux, so kappa n squared.
I don't off the top of my head, but because this is resolved fluxes, then I know I'm not resolved. Like if I were using an LES, like the Hamilton runs, I think that would have been a little more tricky. But because the resolution is such that we're only resolving, you know, even submesoscales, it's like borderline. So I can imagine that most of that is submesoscale induced. But I don't know what the parameters, like it's a KPP parameterization in LLC.
Right. Yeah. So I guess I was asking if like if you were to calculate kappa n squared from KPP, and then you could compare those magnitudes, because if it was comparable, that would be a really nice result. Yeah. Thank you.
I'll look into that. Thank you.
Yeah. Thanks. I'm Moma Hel from Brown University, and I have a question to Helene about CMIP. And you mentioned that the plan is to have ocean, atmosphere, and sea ice kind of on the same grid or resolution. And I wonder if any of the modeling centers have the plan to include surface waves for that.
Well, there's definitely work on. There's
Sorry,
definitely
Helene, you're a
work
little
on.
quiet.
Yeah, no, it's okay. Didn't have the microphone. There's definitely work ongoing to with people to look at coupling surface waves. For example, we've got that in. We're doing some work on that in the metal fist, but only it's it's very much in these sort of things are in development. They take many years. I expect there's similar efforts going on in the States as well. So, and there certainly is at ECMWF because they've coupled waves for a long time. So it's definitely in that regime. Whether that will appear in a CMIP simulation, I couldn't say.
Okay, thanks.
Brody, you're next.
Hi, I have a question for Abby, but first, while I'm standing up here, I wanted to point out that I'm one of the climate match related people. So anyone who is taking photos, if you want to chat about that, me and Momo, who just asked the last question, I can give you information on that. So Abby, I have a question for you, which might convey some of my ignorance for the neural network approach that you're taking. But does this approach produce kind of a diagnostic relationship that's physically interpretable, that you can, presumably, that would allow you to apply it in a GCM and compare to these existing diagnostic parameterizations, the two that you mentioned? Is that something that's possible with your approach, or that you're thinking about?
Yeah, so one of the reasons for testing sensitivity to input variables as part of that is to really understand the sensitivity. So if the skill really deteriorates after you remove the buoyancy gradient, for instance, you know that's like a really key piece of the parameterization, but maybe others are less relevant. And that's kind of one of the first pieces of understanding the sensitivity. There are also methods known as explainable AI, where you can actually it applies a way to basically highlight the regions within the neural network that are learning and what variables they're learning from. So that's equivalent to cracking open the parameterization and understanding really what's affecting what and in which location. So that's also another option. But testing the sensitivity and removing some variables and including all of them, and that's a lot of the work I think that I'm looking forward to really understand the physical intuition behind this.
Thank you.
Yeah.
Thank you very much. I would have a question for Helen. Yes, I found quite interesting the fact that you mentioned the resolution and the point you made about resolution over the 20 years time. And I'm currently based at NOAA. Before I was based in Reading and was working in the Met Office. And I find quite interesting the work that was done on convection, where there was quite a rigorous assessment for convection permitting models. At what scale exactly would the convection yield benefits for the modeling? And I wonder if something similar could be performed for the ERC interaction. So sort of to assess at what scale do we start to gain benefits from the coupling and from the ERC fluxes. Maybe there is no one size fits all, it depends on the processes, but the same could have been said on convection before doing that. Yes.
Thanks. I think that's a really nice idea. And obviously we'd need the model hierarchy. We probably don't have enough of a hierarchy. We're probably not pushing up high enough at the moment with the coupled models. Why don't you ask that question again to Malcolm tomorrow? And he can talk about the hierarchy, the model hierarchy.
So we're getting close to the break, but yeah, okay. Yuri, and then Jim, did you have a question too? And then we'll see.
Quick question to Abigail. I was just wondering if when you look at the layers of CNN, if you have any insight of what the model is doing.
So this kind of goes back to the explainable AI methods I was talking about. So that's something I haven't done just yet. And the first part I'd be really keen to do is to understand the sensitivity to the input variables. But it's essentially picking up the larger scale features and going smaller and smaller. So there's some stuff I was looking at in regards to the spectra and the variability across scales, and there's a very strong correlation to how deep I go. So how many layers I include, we'll be able to learn finer and finer scale features. And then there's a question how important is that for some mesoscales, and what are the dynamics that we're trying to capture? So those are a lot of the questions I'm going to be asking very soon to understand what's relevant for the submesoscales.
Thank you. I just have a follow-on comment. I've heard people talk about machine learning to actually derive new equations, new terms. I think this, I'm not sure if I've got this right, but Laura Zanner was talking about this. You actually find terms in the equation, and her group is looking into it. So that's another very sophisticated way forward.
Okay.
Thanks. Those were three great talks this morning. I really got a lot out of them. So I sort of have an overarching question. I think I'm going to address it to Jacob, but I think it's sort of, I could address it to anyone at this meeting. It has to do with, coupled observational modeling efforts that are going to come out, I hope, of this workshop. So when I parameterize the flux with, say, core, I am parameterizing the turbulent flux. In fact, I throw out anything that looks mesoscale to get that parameterization. So that's been what I've been focusing on for 30 years, right? And here we are now that we're talking about mesoscale flux. And I've seen from these great talks this morning, there's various ways of defining that. But an observationalist needs that because we have to know what we're supposed to be measuring to validate that in your models, right? So it goes both ways, obviously. So I guess my question is, what sort of measurements could you imagine us making that would, validate the models that you're proposing? And this should be, maybe we shouldn't ask this now, it could be a discussion, but that's what I've sort of been sitting in the back room now thinking about for the past couple of days is that. So thanks.
Yeah, I mean, that's of course a big question. We do have observations of sort of these submesoscale features on their own and think we understand how they are forced by air-sea interaction. We, of course, in projects like S-mode are getting a lot more data that includes sort of these fine scales. And then we have the models, and maybe this is part of your question, but I think a big issue is the use of bulk formulas at these scales, because much of our sort of theoretical and numerical investigations assume that we can do that, and that's fine, and it's almost certainly not quite fine.
Hello, I have a question. I've been working for a very long time in small-scale physics of the RSC interface, in particular with freshwater lenses during Toga Code and during the Gulf of Mexico cars in Miami. And what we see, these freshwater lenses start after rain or water from river runoff. They start quickly spreading, almost adiabatically, because mixing in vertical suppressed significantly by density difference. So they become almost like two-dimensional. And we, of course, know that 2D turbulence and 3D turbulence are very different. 2D turbulence has tendency to self-organization. And then if we want to see really how small-scale processes show up on larger scales, we probably have to go to the source of this cascade, inverse cascade, to small scale, but that doesn't seem to be realistic. Is it really a problem?
Sorry, who were you asking, Alex? who were you directing your question at?
Doctor from
Jacob. Fine.
Yes.
Yeah. Thank you. Yeah, I mean, so that is, I think, one of the interesting aspects of considering the submesoscale as a dynamical regime is that it spans the inverse and forward cascade. And that is, a topic of a lot of work right now. It seems that mesoscale turbulence seasonality, for example, is determined by, submesoscales, which grow much faster and are part of the inverse cascade. The sort of symmetric modes that I talked about are probably the most definitive example we have of the forward cascade at these scales.
And of course, submesoscale, small-scale physics will depend even more significantly on the interaction between wind stress gradient and buoyancy. We see it squarely. I have a poster here. And then depending even on wind direction and who knows what your conditions, it will probably have some footprint on larger scales. So that somehow should be addressed, maybe parameterizations, maybe just a question to community.
Thanks very much, Alex. So on that speculative note of thinking about how things cascade up and down and information goes across scales, we're going to take a short break and then we're going to reconvene for the lightning poster talks. Thank you, everyone, for a great session. Thanks also to our remote participants. Feel free to log off.
Thank you.
So we're going to start the lightning poster session now. Richard, are you online?
Here.
Okay, and as with yesterday, just call out when you need to switch to the next slide, and our team here will advance for you.
Okay, fine. Thanks very much. Hi, my name's Richard Hall from Imperial College in London, and I'm working in collaboration with NCAR and WHOI on Oyashio variability and large-scale air-sea interactions. This is a bit of fairly preliminary analysis, but it's thrown up a couple of interesting points. We're defining the Oyashio by looking for an index, and a commonly used index is using a principal components-based approach to sea surface temperature gradients in the Oyashio region. And when you define this index using different SST datasets, so for example from ERA 5 or the OI dataset, then the time series that you derive from those are shown on the right. And actually, you can see that whereas in some years the time series converge, on multi-annual scales there's quite good agreement, at other time steps there's quite a discrepancy between the different time series. And if you look at this on a seasonal basis, then the correlations are actually poorest in February and March. Correlations can be as low as 0.3 between different data sets. So this has quite important implications when, for example, the index is used in regression against atmospheric variables or sea surface temperature, because the indices are not actually as similar as we might think. So on the left, this is the sort of simplest regression map you could get, really, just regressing the indices from ERA 5 and the OI dataset against sea surface temperature. And you can see that, okay, there are broad similarities, but actually there's some significant differences as well. So for example, in the lower part of the plot for the OI, the positive values are shifted to the south. You have more extensive significance in the negative values, particularly to the north of the OI region, whereas ERA, you may argue that the signal is perhaps more intense in the OI region. Now, actually, this is not the best example, but it's just the simplest one. But if we take other variables and we take different leads and lags, and we use high-pass data, for example, or we look at the asymmetry in the relationship by regressing the negative values of the index and the positive values of the index separately, then the discrepancies can become much, much greater between the different data sets, which obviously leads on to questions about how you interpret the regressions or similar analyses when you're looking at air-sea interaction. So next slide, please. So all the data sets essentially show a similar sort of configuration of SST fronts. If you look at the top plot, then it's what you've got in the Oyashio region to the west and to the east, you've got quite clearly defined fronts. But then in the center, between 155 and 160 east, you've essentially got two parallel fronts. And then in the next little section along, you've got a broader region, I call it a diffuse region, where the front isn't very clearly defined at all. Down at the bottom, you can see box and whisker plots showing where the maximum gradient is, the latitude of the maximum gradient. And you can see again, those two regions are highlighted, the double front region between about 155, 158, and then the shallow region around about 159 to 163. And you can see here that sampling's taking place from both of the fronts within the double front region and across quite a broad range of the shallow front region. So very, very slight SST gradient differences in the different data sets can actually suggest a front at a different latitude, which can then throw up these different indices. So you can't see this just looking at the SST fields, and the differences are very, very subtle, but it really hinges on these two central regions. So essentially, we've got an issue with front identification where the SST gradients are complex, and this has implications for interpreting the results, particularly if you sort of rely on an off-the-shelf SST data set and perhaps don't realize that you would get a different pattern from a different data set. We could use an ensemble approach where we look at the different data sets, we look at the regressions, and we can identify common features. But another possible way forward is the GMPE, which is a multi-product ensemble, because when you derive slightly different versions of the indices, then that tends to identify quite robust features across the different versions of the index, whereas some of the other data sets can produce widely differing results. There's more information on a poster if you want to have a look at that. And another possible way ahead is we're trying to quantify this uncertainty, because there's a suggestion that the degree of uncertainty here also has an important physical impact on air-sea interaction. Thank you very much.
All right, thank you, Richard. Our next talk is from Brian Arbick.
Hi, thanks everyone. I wish I could be there at the meeting, but I'm teaching a new course for the first time here at Michigan. So I'm going to talk about 3 topics of interest for satellite missions and models focused on air-sea interaction and mesoscale processes. And I'm examining all 3 through the lens of high resolution models. So the first one is simulation of near surface internal gravity wave kinetic energy, specifically near inertial motions. So surface flows are an important variable in air-sea interactions, and the Arbick et al. Paper shown on the left, the DOI there, we compared near surface kinetic energy in 2 state-of-the-art global high resolution ocean-only simulations with observations from undrogued and drogued drifters, which respectively represent flows right at the sea surface and 15 meters below the sea surface. And we did that in many frequency bands. So it's quite a comprehensive paper. Please take a look. But in the plot on the right, we look at the impact of coupling to an atmospheric model. So we're showing the zonally averaged near inertial flow at 0 and 15 meters in drifters, and 2 versions of the MIT model. If the MIT model is forced by 6-hourly winds, you get the green curve, which is quite weak compared to the red curve, which is drifters. That's both at 0 and 15 meters. But if you take that same MIT model and couple it to an atmosphere model, the much more frequent coupling inherent in that gives you the blue curves, which is much closer to the observations. So it means that an added benefit of a coupled model is that you get much more accurate near inertial motions, which are a very important part of the kinetic energy near the sea surface. Next slide. So point number 2 is about high frequency precipitation variance. So Covey et al. Showed that most precipitation variance is in sub-daily timescales, and that low resolution climate models do not capture that high frequency activity at all. So in a paper that was published last year, I'm proud to say led by an undergraduate, he demonstrated that models with high resolution in the atmosphere produce more high frequency, including sub-daily precipitation variance as in observations, and that the ocean model resolution also matters, especially when the atmosphere model itself has high resolution. So the plot below illustrates these points, and I don't have time to go over it in detail here, but I have a poster. So moving on to the last point, the proposed Odyssey mission will measure sea surface velocities. And so we did a little OSSI experiment with the high-res coupled ocean atmosphere model to look at spectral kinetic energy fluxes. Spectral K fluxes show which way the energy is moving around. Myself and others have written several papers about computing these using geostrophy applied to sea surface heights. Odyssey would measure them directly from velocities, and so you could estimate the fluxes, including the ageostrophic parts. So really quickly, the black curve is showing the spectral Ka fluxes computed from the model, so that's taken as truth. The magenta curve is with Odyssey time sampling. You can see that it's hardly any different. And the blue curve is with estimated instrumental noise from Odyssey, and it's still not that different. So the answer to the question is yes, you should be able to use Odyssey to estimate this fundamental quantity, how energy is moving around in the surface ocean. Thanks.
Thank you, Brian. Next up, we have Solange Cordu.
I'm Solange. I'm working at Laboratoire de Météorologie Dynamique in France. I'm a first-year PhD student, and I'm focusing on ocean small scale. So at the moment, I've been looking at data collected during the Eureka Ocean Atmosphere campaign that took place in the northwestern tropical Atlantic in winter 2020. So here you've got a picture of the chlorophyll satellite map from during a day during the campaign, just to highlight what are the main scales that we can expect in the datasets. Just to give some context, so during the campaign there was a freshwater plume coming from the Amazon, which was channeled and steered by the mesoscale eddy field. So I'm using data from 5 cell drones. They have a 1 minute sampling frequency, which gives me quite high resolution data with about 80 meters spatial resolution. So on the right, on the top panel, you can see the entire time series of 1 cell drone. So density, salinity and temperature have been density scaled. So you see that temperature is approximately constant during the cell drone journey, oscillating around 27 degrees, whereas salinity presents really big lateral variation. And you clearly see that at large scale, looking at the old time series, salinity is driving the density variations. Whereas if you have a closer look on smaller pieces of this time series, you see that the temperature is not really constant and compensate the salinity variation at smaller spatial step. So this kind of scale dependence of the compensation between temperature and salinity was looked into further detail using wavelet transform analysis. You can move to the next slide, please. So this was for the surface, and then the question was, how does this signal extend at depth? So unfortunately, we don't have any colocalized data, salinity and temperature for these cell drones. The only information we got from the upper ocean is through the ADCP that they were carrying on their keel. So first, we have seen that we can kind of relate the maximum velocity shear, vertical shear level with the mixed layer depth based on some temperature salinity clustering and using vertical profiles from other in situ data collected during the campaign. And so on the plots on the right, so in red, you've got the vertical velocity shear, and you see that where you've got strong salinity jump in blue, it's usually correlated with a sharp increase of the maximum velocity vertical shear level. So the mixed layer depth is very shallow at these places. And you've got this signal when you crosses the plume or the edge of the plume, but also on some eddies that are referred in the region as North Brazil current ring. So you see that the plume has kind of cape the eddy surface. Thanks.
Thank you, Solange. Next up, we have Philippe Touchen.
Yeah. All right. Hi, everyone. This is Philippe Touchen from NOAA PMEL in Miami. I'm going to jump right into my slides. So as you can see from this map of satellite-derived SST anomalies from last year during one day in August, both the equatorial Pacific and the equatorial Atlantic mesoscales are very much dominated by the presence and propagation of tropical instability waves that we can see here as these wave-like structures of anomalously cold water near the equator. So in general, tropical instability waves are thought to be an important component of the equatorial heat budget, and they're also known to cause complex injections and feedbacks with the atmosphere. Next slide, please. Good. So tropical instability waves, they have very distinct variability patterns on intra-season timescales in many variables such as SST, sea level anomaly, and meridional velocity, which is shown in the upper left figure. In a study that we recently published in GRL last year, we find a multi-decadal intensification of tropic instability wave activity in all of these 3 variables and even more variables. Most pronounced is the increase in TRW-induced SST variability over the last 40 years, which increased by more than 40%. There's also a lot of interannual modulation, which I don't have time to talk about. And I also don't have time or enough time to talk about what did cause and what did not cause this intensification. But I can refer to you to our paper, which you can access through this QR code here, or to my poster in the online gallery for a more complete discussion. But I can very briefly say that we also see increased barotropic energy conversion as a top candidate for the reason for intensified TRW activity. One thing we also noticed in our analysis was that near the near surface velocity variability on the equator is very much underestimated by the gridded products that we looked into, such as OSCAR, the geostrophic velocities from AVISO, from altimetry, and also from a drifter altimetry or drifter wind altimetry synthesis products, which all underestimate the observed meridional velocity variability, which we know from mode observations on the equator. So this is the bottom right plot here, where you can see, just as an example, 1 year of measurements and the difference between the gridded products and the observed or the in-situ observations. And this is why we really want to point out in this study the importance of in-situ observations and recommend at least maintain, even better to expand the observations close to the equator. And this will also be a very useful tool to support and validate satellite missions in the future with a focus on surface currents. That's all from me.
Thank you. Next up, we have Andrew Delman.
Hi, yes, I'm Andrew Delman at the UCLA and JPL. I'm going to talk a little bit about the work that we're doing, developing a framework to look at the contributions of mesoscale dynamics to surface variability, and in particular to the mixed layer temperature budget. And I see this as complementary to a lot of what's happening at this workshop, where there's attention to the coupling at mesoscales and submesoscales. Really, what I'm focusing on here is the role of ocean dynamics in influencing surface parameters like SST. So how we're doing this is, but you take a temperature budget, and the focus that you have is the ocean dynamics and the influence of the temperature flux convergence term. So that's that first term on the right-hand side of the equation. And we decompose the advection term, the 3-dimensional velocity and the temperature, using a 2-dimensional spectral filters. So there's an example down here in the lower part of the slide to see what this looks like with surface velocity, zonal velocity, or model U velocity. If you look at this snapshot down by the southern tip of Africa, you have a area where there are a lot of meanders and eddies and all this sort of mesoscale dynamics going on, and so you can apply these filters, and so you get a large scale velocity, which kind of shows the eastward flow of the Agulhas return current at ACC, and then you get a zonally elongated component, which is where the dynamics are mesoscale along one axis and the other, and that they're zonally elongated. And this represents a lot of planetary waves and also zonally oriented jets. You get another kind of elongated component which highlights western boundary current jets that aren't zonally elongated, as well as a lot of the meanders that you see. And then finally, there's the non-elongated, or the isotropic component, which is focusing kind of the vortices, or what we often call eddies, canonical eddies. Next slide, please. Yeah, so I'd hope to extend this analysis to a longer time scale. I kind of got caught up in some methodological improvements instead. But I'm showing this these effectively snapshots or 5-day averages of impacts on temperature tendency from certain components. So on the left panel, you have a temperature tendency. That's all of the affected advection, the temperature flux convergence. And we applied a low pass spatial filter to all the terms to just kind of smooth the patterns, make it more visible globally. And so, in the total temperature flux convergence in this time, which is in boreal winter, you have these a large dependence on latitude. Some areas advection tends to cool, some areas tends to warm. So then if you exclude the large scale term, which is just the convergence of the product of large scale velocity and large scale temperature, you take away a lot of that kind of latitudinal dependence, the latitudinal banding, and you start to see more of what's happening in areas where we know that there's a lot of mesoscale activity and energetic currents. And then if you focus only on the terms that are what we call eddy, the parts with the non-elongated component, you see some of the rest of the mesoscale influence removed, and what remains is that you have significant warming impacts in places like the Kuroshio extension. Some interesting patterns that you see in the Gulf Stream and North Atlantic Current and around the southern tip of Africa again. And I'll note that one of the things they're finding is that it's you expect that the eddies are going to move heat down gradient, like you generally in the kind of Ghent-McWilliams parameterization. That is what you expect eddies to do, and that is often the case, including the Kuroshio area. But it isn't necessarily the same. These aren't the patterns that you see in that right panel are not just temperature moving from or heat moving from warmer to cooler areas. So there's a lot to unpack here, and so as we're looking to extend this to longer timescales, especially the interannual and decadal influence of mesoscale ocean dynamics to SST and therefore the possible influence on climate, and also to adapt the budget and the filtering code that we're using for use of the Arakawa seaweed models, such as MIT GCM, which is a particular interest with the ECHO project. So thank you very much for your time.
Thank you, Andrew. Next up, we have Rick Danielson.
Yeah, thanks to the organizers for hosting this sort of applied observational study on an estimated 340 North Atlantic right whales that are alive today. About almost half are foraging in the Gulf of St. Lawrence when sea ice is absent, and whereas whale presence is a great indication of zooplankton aggregation. These zooplankton are these little rice-sized pictured images of above the whales here. Proxy signatures of aggregation in synthetic aperture radar is not well known. Submesoscale dynamics motivate the use of filamentary patterns that are nicely revealed by SAR contrast, which we define at upper left as a ratio of the SAR backscatter sigma naught, where the overbar is a spatial mean. So dynamical models of radar backscatter provide a dependence of SAR contrast on ocean surface currents, which modulate wave breaking, for example. But the light winds are known to be favorable for visualization of current boundaries. So if we want to explore SAR filament patterns near right whales, but we expect SAR contrast to depend linearly on wind speed, the poster, or the topic here is designed to try and understand how we could compensate for the wind dependence. And radar scattering models are like the primitive equations of our numerical models. So in that sense, they're not measurement specific, say. So by design, they apply to all the relevant measurements that that they pertain to. So our observational study begins by defining the measurements first, the measurements of interest, and then approaches the question of dependence by asking how specific SAR and wind measurements are associated. And for this, we define a set of quote unquote primitive equations that looks like a statistical model in the purple box. But here we're using a slightly more complete set of terms for a trichotomy of associations where there's linear and nonlinear and lack of association in there. It's explained in the poster, but just like a conservation of mass, force, energy, or entropy, or the temperature budget that Andrew just showed, everyday primitive equation models, even those with residuals, have a signal and noise term where our interpretation is of the signal. So just like that, we're trying to apply signal interpretations to our signal and noise terms, and there's no add-on terms for error or uncertainty in this. We don't have an interpretation of. So our poster provides some details about total nonlinear association, as well as distance correlation, which is an aggregate measure of nonlinear and non-monotonic dependence. It's a newer measure of correlation. So with these aggregate and term-wise measures of nonlinear association, we seek to maximize the correlation between SAR contrast and ERA wind speed to some power. And since both Pearson and distance correlation can be maximized for our three domains, it implies that there's a partial adjustment of SAR contrast that's possible by some simple and inverse SAR weighting by wind speed to the power of here 0.8 perhaps. So in particular, this helps to highlight SAR contrasts in the Shediac Valley, where that's the lower domain in the green plot, where North Atlantic right whales are most commonly seen, and wind speed tends to be higher, but SAR contrast is weaker. And it doesn't, the poster doesn't answer the question of what a SAR signature of zooplankton is, aggregation is really, but it seeks to better isolate the coherent current boundaries across a scene, a given SAR scene, or across a number of scenes. Thanks.
Thank you, Rick. Next up, we have Arpita.
Yeah. Hi, everyone. I'm Arpita from NOAA AOML and CMIP University of Miami. So it is well known that the northwestern tropical Atlantic Ocean in particular is a breeding ground for devastating tropical cyclones. These cyclones are also prominent upper ocean mixing agents. In this region, freshening from rainfall and especially river runoff causes salinity stratification that can reduce sea surface temperature cooling in the wakes of the tropical cyclones. And this reduced cooling makes rapid intensification of tropical cyclones more likely. So the impact of tropical cyclones on heat transport and circulation has been explored so far, but there is very limited understanding of the impact of tropical cyclones on upper ocean salinity transport and circulation. So our research question is, what is the role of tropical cyclone induced salinity variability in the physics of the upper ocean? So to answer that, the surface salinity signature and the vertical structure of salinity wakes on various time scales are investigated using data from Argo floats and satellite observations. So over here, there is a map that we see, and it is a map of sea surface salinity wakes prepared using Argo floats 2 days after tropical cyclone passage for tropical cyclones present during the years 1996 to 2021. So red indicates a saline wake here, while blue indicates freshening. And as we see, there is a saline surface salinity wake in the Amazon plume region and in the northern Gulf of Mexico, and while there is a fresh wake in the southern Gulf of Mexico. So focusing on the Amazon plume region, on the bottom right, this is a composite of the vertical structure of the wakes in the upper 100 meters of the ocean. So we see that a saline surface salinity wake and a subsurface freshening dominate here. On the left, there is a vertical profile of salinity that shows the state of the upper ocean before a tropical cyclone. So as seen, the surface is very fresh here as opposed to the subsurface. So mixing down of fresh surface waters from river runoffs and in the Amazon plume region and the upward advection of salinity maximum water possibly explains the salty surface wake and the subsurface freshening in this region. More details on this are explained in the poster. This work is going to continue by expanding the analysis to other basins with dominant tropical cyclones. And yeah, so for discussions and feedback, please reach out to me on my email ID that's given over here and also in the poster. Thank you.
Thank you very much. Next up, we have Doug Vandemark.
Okay. I have the topic here of using SAR to diagnose boundary layer stratification change at the ocean sub to mesoscale. And I tried to put this in terms of a discussion question tied to the workshops, talk about analysis approaches and diagnostics of air-sea coupling, which could guide modeling and observational strategies. And the question I posed was, could such stratification information from global satellite SAR data be useful diagnostic for some of the objectives coming out of this workshop? And so what we have with this result on the right is we're using the Sentinel-1 SAR satellite, which is providing global measurements of these small imagettes, 20 by 20 kilometer pictures of the ocean surface from the synthetic aperture radar that had a little bit different scale than what Rick was just talking about. We see the atmosphere, the boundary layer, coherent structures very often give us a picture of these three states. One is the microcell convection on the left. The middle one is roll vortices that span the boundary layer in the middle. And then another thing that we've run across that we weren't really looking for was when you have warm advection in a synoptic system, for example, we end up with no coherent structure in the stable boundary layer. And so we're mapping this thing up on the right here up into the cells in the Richardson number are showing unstable stratification. The wind vortices fall in the near neutral in the Richardson number, and these lack of coherent structures are giving us stable boundary conditions. And I guess you can give the next slide. And just as a couple of examples, you can map these coherent structures on the left there between this kind of unstable cellular up on the upper left to the near neutral wind streaks in the middle, and then stable conditions on the left against what you see from the ERA5 reanalysis Richardson number, for example. And look at, we are able with 8 years of data now to look at things like stratification change across, for example, long-lived eddies and or the mesoscale western boundary current of your choice. And then on the right, this is just a zoom in of these 20-kilometer snapshots. We're focusing on that atomic URIC 4 region right now and looking at these data. And these are within 20-kilometer changes across air mass boundaries or ocean fronts, where you can see the coherent structure changing across boundaries. And so this just goes to the point of having a global data set related to stratification that might be useful. So thank you very much.
Thank you, Doug. Next up, we have Rianne.
Hello, my name is Rianne Giese from the Netherlands Meteorological Institute. Our poster is about different applications using remotely sensed winds from scatterometers to correct for persistent biases in modeled ocean surface winds. So an example of these persistent biases here for meridional winds is shown on in the figure on the right. This is an annual mean biases between METOP A ASCAT winds and ERA5 reanalysis winds for 1 year. And the upper plot shows the bias in the mean wind, which can still reach values up to plus or minus 1 meter per second, averaged over 1 year in some regions, particularly in the tropics. And the lower figure is for the transient wind, which shows that there's a lack of small-scale variability in the ECMWF model winds at all, actually on a global scale. And we propose a method to correct for these biases using temporally averaged differences between scatterometer observations and collocated model winds. So this is done on a local scale. So for every grid cell, we calculate the difference and average them over a certain time period, which is typically in the order of a couple of days. So it's not correcting for the really short-lived events that are maybe not well captured in the model, but more for the more persistent biases that can be related also to representation of processes in the model. Next slide, please. And on the poster, we show 3 applications. Next slide, please. Yeah, thank you. Of these scatterometer corrections. So the first is that we have produced a new wind products for the EU Copernicus Marine Service, which provides free products to use for any user. And these products provide the hourly ECMWF surface wind and stress fields, which have then been corrected using scatterometer observations. And the products provide both the corrected fields and also the bias correction. So users can always go back to the uncorrected fields. And next to the surface wind and stress components, it also provides the divergence and the curl of these fields. And the second application is using machine learning to to connect these scatterometer corrections to other variables, oceanic and atmospheric variables. So different machine learning setups are explored to find functional relationships between a set of variables. And well, this is still a preliminary results, but they look promising. At least the models are able to reproduce these scatterometer correction fields, and they can then be used to correct for biases for in periods when there's no scatterometer observations available. So then when the corrections cannot be calculated from observations, which can be, for example, for forecasts, and also for periods longer back in time when there were no or very limited scatterometer observations available. And
1 minute, Ryan.
Yeah, thank you. And the third application is actually a bit the other way around, actually applying the bias correction to the scatterometer observations. And this is done because the large systematic errors in the model winds actually inhibit the assimilation of scatterometer winds in the analysis of the model. So to actually, by subtracting the correction from the scatterometer observations, we actually nudge the observations towards the model state, and it's expected that this will be beneficial for data assimilation. This is still to be tested. We're currently performing an experiment with ECMWF to see the effects. Well, there's a little bit more information on the poster, and if you have any questions, please feel free to contact me. Thank you.
Thank you. And on to our next talk is Jin Long.
Hi, Kelvin. Yeah, hi, my name is Xin Liu, and I'm a PhD student at the University of Tasmania. Today, I would like to show my work prepared to my PhD. Characteristics and trends of the Campbell Plateau meander in the Southern Ocean from 1993 to 2020. This figure shows the meander's mean positions over 3 different decades, using black lines and monthly positions in every 10 months using yellow lines. 4 peaks with white circles and 4 troughs with white triangles are marked along its trajectory. We also separate the meander into 3 sections by the white vertical dashed lines and highlight a flat region by the white dashed rectangle. In this study, we find that the Campbell Plateau meander has clear trends over the past 27 years. The meander has been overall spatially fixed, but downstream from the plateau, moving northward, the meander has been flattening upstream from the plateau and flexing downstream from plateau. The meander has been widening and accelerating, especially upstream from the plateau. The Campbell Plateau meander also has similar trends with the Gillis-Cleveland sandy meander in position, amplitude, width, and speed. Next slide, please. This figure shows the monthly time series by solid lines and corresponding linear trends by dashed lines between 1993 and 2020 of the Campbell Plateau meanders position, width, and speed. Different colors represent different sections of the meander. Positive trend values in the position, width, and speed mean the northward movement, widening and accelerating, while negative trends indicate the southward displacement, narrowing, and decelerating of the meander. Those statistically significant trends are labeled with star. To explain the northward movement of the meander's downstream section, we have 2 hypotheses. First, changes in the stability properties of the downstream jet. Second, changes in the South Pacific jet. The meander has also become wider, and this is consistent with recent studies. We assume that changes in the meander's volume transport may drive its widening trends. We also have 2 hypotheses to explain the acceleration of the meander. First, the intensification of mid-latitude westerly winds, and second, the increased buoyancy forcing. This is the end of my presentation, and thank you for listening. Please email me if you want a further discussion. Thanks, Helene. That's all.
Thank you. And then we have our final lightning talk from Sana.
Yes, hello, hi. So I'm Sana Mahmood, and I work at the UK Met Office, and I work in the Regional Model Development Team. And I want to introduce you to the Regional Coupled System, which is a system that's been developed by many people. And this system allows us to run many different experimental designs, from fully coupled to component only. It's a complex system, so this figure kind of shows that. So we have a regional atmosphere model, which is a unified model with a land surface model, and we can couple it to a NEMO ocean model and also to a WaveWatch 3 wave model. And all these different variables that I've got here with the arrows can be exchanged. There's a range of user options, so we can run over different model domains. So predominantly we've done work to run over the UK, but it's relocatable, so we can run over other parts of the globe. And we can also run with different grids, so with different resolutions. We run deterministic forecasts, so just one simulation, but we've also done some recent work in which we've been running ensembles over the UK. Also, some recent work has been trying to get this to run in a climate simulation mode too. Things under development are we're trying to add a biogeochemistry component, and that's work being done with the Plymouth Marine Laboratory, and also including modelled river outflow into the ocean. Next slide, please. So I've just picked out some highlights. So you can find further details of these in the poster and also further examples as well. So on the top left, I've got some work that's been done by Claudio Sanchez, and he's run the regional coupled system over the Mediterranean, and he's run experiments in which he's added plus or minus 2 Kelvin SST perturbations, and he's seen that he can improve or degrade the predictability of Mediterranean Llanos. And then, as I mentioned, we've had ongoing developments of climate capability, and this is work by Alex Arnold, and she's been running atmosphere-ocean coupled climate simulations over the Northwest Shelf. So she's got 5-year hindcasts that she's run, and there are plans to do present and future runs using atmosphere-ocean waves, so fully coupled, and also including rivers too. On the bottom left, this is work in which we demonstrated that SST evolution over 5-day timescales can impact the air temperature over land in the UK. And as a result of this, we have now implemented in our UK operational weather forecasts, we now have time varying SST rather than the traditional fixed SST. And then finally, the last panel is work by Juan Castillo, and he's been setting the system to run up over India and looking at how well it represents tropical cyclones. Thank you.
Thank you, Sana, and thanks to all of our lightning talk presenters. We can get another round of applause. I don't know if they can hear it or not, but the spirit's there. So we're going to break for lunch and then reconvene. Sorry, let me look at my agenda at 1 p.m. Mountain Time for our observational session. Thank you, everybody.
Good afternoon, everyone. Welcome to everyone in the room and everyone online. We've got a great session now for the next 4 talks on state of observational capabilities. We're going to run through all of the talks and then we'll have a good 20 minutes for discussion at the end. So first up, I welcome Jim Edson. Over to you.
All right, so might as well get started here. I am Jim Edson. I'm a senior scientist at the Woods Hole Oceanographic Institution. Recently, well, it's not too recently, I've been at this for about 8 months. I'm also the PI of the Program Management Office of the Ocean Observatories Initiative. How's that for a mouthful? I've been at that since March 1st, so it's been over a year now. So I'm looking forward. This talk was fun to put together because there's so many cool platforms out there to describe to you folks. I want to make it very clear, and so this is, I've done this work with numerous colleagues, and you see I've included just about every federal agency you can include on your intro slide, because they've all had some part in funding this research. I want to make it very clear, though, because I just thought of another platform I could have added to this talk. This is by no means inclusive, the platforms, okay? So please don't feel slighted if I don't describe your favorite platform. We can talk afterwards. So without further ado, so what I've been doing for probably the past 30 years or so is gotten pretty good at making these direct covariance measurements from sea. And these, this is not an easy thing to do, particularly you'll see on moving platforms. So what we typically do is we develop bulk parameterizations by measuring the flux, first of all, directly and with these other mean variables, and then we can parameterize the transfer coefficients. The one you're probably most familiar with is the drag coefficient, and I'll mention that occasionally during my talk. Now, this was the point I was trying to make at the previous session. These fluxes are turbulent fluxes, all right? And I go to great lengths trying to remove mesoscale noise out of my turbulent fluxes. So these parameterizations are for turbulent fluxes, and that was why my question, right? Now, so moving platforms do require correction for platform motion. That was first done here on ships. That's the toga core. I don't know what that is. And yeah, thank you. So that's the Moana wave that I was on during toga core, and we continue to this day using ships for flux measurements. However, ships. Here we go. Oh, I'm sorry, I didn't notice that. Ships, by their very nature, are big, bulky things. There's no getting around it. They generate flow distortion in your measurements. That makes flux measurements from ships, direct covariance flux measurements from ships, difficult. So a few years back, I started just to focus on these surface moorings that are much lower profile and much less flow distortion. And that includes the ACIT spar, and this is the CLIVAR buoy. That was the first deployment where we made direct covariance fluxes for over a year. And then we've been adding capabilities ever since. And so, for example, that spurs mooring was the first time we put an infrared hygrometer on a mooring and ran it for a year. And we got amazing latent heat fluxes to go with the sonic buoyancy flux, which allows you to measure the sensible heat flux as well as the latent heat flux. So that's a goal. We'd like to have that on more platforms. But we've also been working with platforms where all of these here, where we get real-time data back, where we actually do the flux processing on the buoy or platform and telemeter it back via, say, Iridium to shore. So you're gathering research quality data during the life of the deployment. That was the idea, and it works pretty well. So let's just start with ships, because we're still using ships. They remain a component, important component for air-state interaction research. They do support instrumentation to estimate the fluxes, bulk and DC. But I think more importantly, they support system for remote sensing of the marine boundary layer. This is, I think Elizabeth may remember this plot. So this, whoops, that's from the C-band precipitation radar on the top. This is the Ravel. This was the amazing imagery that we got from that during the Dynamo experiment. And also we've had scanning LiDARs on there. Here's a W-band radar. We put ceilometers on these ships. So, and of course, they're very convenient platforms for launching balloon. And Caroline Clayson here will kill me for showing this picture, but so be it. That's her launching a balloon. So we still work to measure fluxes from these vessels, but because of the flow distortion, it's problematic, all right? And so we can minimize the influence of flow distortion by optimal placement of sensors, and for the most part, that's up on the forward mast of the ship. Empirical corrections for flow distortion on the mean wind, and for example, we've used the scanning LiDAR measurements looking in front of the ship at say 10 meters elevation, and then relating that to the measured wind speeds. And it's a really nice way to come up with an empirical correction for flow distortion. And we've also used some of these new methodologies to reduce the flow, such as this paper here, which actually allows us to make these measurements when we're on the move, which was a really useful thing. And so just to sort of point this out, so the blue here is 15 months of buoy data in blue. The red is about 6 weeks of ship data. You can see in the mean, there's not too bad of agreement here, particularly in the moderate wind directions, but we do start to see something going on at high winds. And also you can clearly see that these are just standard deviations are substantially larger for the ship than on the buoy. All right, so here's the thing that is difficult with ships at times, and that is the transects. So I was able to work with the oceanographers during the Climode pilot cruise, where I said, well, why don't we just do this cool sawtooth pattern, sorry. This sawtooth pattern, because this is the Gulf Stream, all right here, the Gulf Stream front. And you can see the wiggles are where we stop for CTD casts. And we launched balloons when they were doing CTDs. And we got a nice data set out of that. It was a pretty short cruise, and the winds didn't really cooperate. Oh, well. Well, it was better than this. So this is when the oceanographers went feature hunting, all right? And and so, when the wind's blowing up from, aft to forward, there's nothing we can do. We can't measure anything. So we tend to throw out about half of our data because of that. Nothing we can do about that. But maybe if we, and so that one, oops, I just want to show this one spot right here is where our graduate student found a crossing with good relative wind directions where he could look at these atmospheric profiles here as we go across the front. And you can see a deepening of the boundary layer as you go from cold to warm water. Now, the cruise, I think, needs to be dedicated to air-sea interaction. Wouldn't that be wonderful if we had control of the ship for our experiments? Now, ships are also very good at deploying moorings. So this is a spurs mooring. I like to pretend that I know what I'm doing. That's me handling this all-important tagline. It's up to me. So here's what we typically do. Now, I don't know if you can see it. You can't see it. Take a look at me doing this back bend. That's because this tagline was pushing the sonic forward, and it pushed it about that much. And so I was looking at it going, oh man, guys, because they were just worried about getting the damn thing in the water, not about the instruments. And so I'm looking, you can see I'm scrutinizing. And so, right? And so I went back inside. The data was still coming. We were telemetering it. It looked okay, but I used it as an excuse to go for a boat ride, which is always fun. So that was me swapping out the Sonic after we had deployed it. Now, this is just a good slide to show that these are the basic components that we use to measure these fluxes, a 3D Sonic and an IMU for motion. And this is one of those cruises where we added an infrared hygrometer so we could get the momentum, heat, and mass fluxes on this particular cruise. Now, I would say tropics is for wimps. Real scientists go to high latitudes, and so this is what I mean by that. So this is the Erminger Sea mooring. It is off, this is Greenland. That's where the mooring is located. I forget which one of these is the surface mooring. It doesn't matter. It's one of them. The other is subsurface. And you can see this is a brutal place to make measurements. But when you make the measurements, they're incredible. These very high wind speed measurements. And so you can actually see that on this. This turbine is spinning freely. That one's not doing so much. So we had about half the power we normally get from those wind turbines. So in order to do the motion correction, you need you need this package that's all in that oval up there, 3-axis Sonic. So that's what gives us the U observed. The B, which is the angular rate sensor, gives us the omega cross R. That's the angular velocity. The transformation matrix really comes from all of the sensors combined, and that's to transform it to vertical every time step before you make your measurements. As is the accelerometers are integrated to get the high pass filtered velocities. And very importantly, as this group knows, you should make your measurements relative to water, and that requires a current meter. Here is my best example of why you need to measure relative to water. This plot shows the winds relative to Earth, and this plot, the red is when we were in the Gulf Stream, the blue is when we were out of the Gulf Stream, and you can see there's quite a bit of difference between those two. If I put it into a water relative frame, it looks like that. So this is the most striking example I have, that relative to Earth, relative to water. We need to be relative to water, and we in this room, everyone understands that. So moving on, this is just to show you that I think this works extremely well. These are all of the sites, either as part of the WHOI or research deployments. This is the WHOI high latitude mooring in the Erminger Sea and Papa. And if I compute the drag coefficient from all of those different sources of data, the parameterization I came up with 2013 is in red, and the parameterization with all that additional data is in black. There's really very little difference, and I'll be tweaking the high winds, basically. So what's going to happen. Okay, just another platform that we're kind of proud of is this XBAR. This is about as low distortion platform as you can build. And this one, I know that we've, whoops, let's go back. I know that we've gotten the motion correction right because these are real-time data from the mooring. This was in the North Atlantic in the Erminger Sea. It was floating, and it lasted for about 3 months. The X and X bar is expendable. It's expendable because we can compute the fluxes on the fly and telemeter to home. So you could lose this thing. The idea is you could put this in rough areas like this or the Southern Ocean, even better, and let them drift around. Because this will run for about a year on the batteries that we have. And so here you can see, it was actually recovered. We never thought we'd see it again. That's what happened to it by being in the winter Erminger Sea for 3 months. It was kind of a hazard to navigation, so we're glad that the Coast Guard found it. The next version, we're going to be able to scuttle it with a button, is the idea. So we don't have something like that floating around. So let's move on now to the horizontal variability using uncrewed surface vessels, USVs. We know about sail drone, and we're going to have a talk, I believe, at some point today about sail drone. I'd like to just mention some of these other. So this is an autonomous boat, basically the jet yak. There's other groups that are operating these, and there it is in slow motion, actually. This thing can get up to about 20 knots. So it can zip. it's short duration, it's gas powered. I think it's 8 hours is it's how long it lasts, okay? But this thing is great in Arctic regions. It doesn't do too well in big sea states. You can imagine, it'll spin over. The other thing, really useful platform that, you know, I think most of us are aware of is these wave riders. I believe this version is from UW APL. So it's wave power, it has long duration, it's not so fast, but it runs and runs and runs, and it's impressive some of the patterns that this thing will keep. This is it in action. Thanks, Luc. I don't know where Luc, there's Luc in the back here. So this is what it looks like when it's deployed, and I want to just point out, this is an amazing result right here. There are people that don't believe buoy data at like above 15 meters per second, where you're about 5 meters above the ocean surface. This is 1 meter above the ocean surface. And it's being compared to FLIP, which is not moving up and down very much. And you can actually measure at 10 meters and you get this amazing agreement. That's astounding, I think. Now, these are bulk fluxes, and I'm a little leery of trying to do direct covariance on these platforms, but certainly bulk would be wonderful with these sorts of measurements. So I hope I've done you justice there, Luc, but I think it's great. This is the star of the show as far as I'm concerned. This is something that I saw when I was in France about a month ago at a POGO meeting, and there was an outfit there. This is a French outfit, and this is just really impressive how it's plowing through. I think this is a Sea State 5 that it's plowing through. And so this thing can run, it's diesel powered, right? It's got a lot of juice. It can run for 7 days duration at 7 knots, and then plus or minus depending on how fast you want to go. They're currently using it for mapping. Larry Mayer up at UNH, some of you are probably familiar with. He's bought one of these and is using it, has wrung it out. I think he really likes it. And you can, you know, of course, when I saw this, I said, I could put a sonic on that, right? And so that's the idea. I would love to put a sonic on this. It has the motion really well characterized. And so really it's just getting those velocity measurements on it. So anyways, I like this platform. Now, you guys are probably very familiar with gliders and AUVs. These are terrific platforms for mapping out horizontal, well, actually in 2 or 3Ds, depending on how long you go. So these are buoyancy driven, the gliders. They have long duration. They're pretty slow, right? The Remus AUV, which is WHOI, there are other AUVs on the market. It's battery powered, fairly short duration, but higher speeds, and they can do more complicated transects. Here is our crewed, and it should say crewed or uncrewed area vehicles, UAV. I told Chris Zappa that he would get 15 more seconds of fame on his video. He showed this yesterday. I thought it was so cool, we'd show it again. Luc's group at Scripps is using one. They use the launching approach and then a tail hook to get it back on board. And he assures me that they get data more often than not when it does. It's a little violent, that tail hook thing, but Luc says it works. And so we've got 2 approaches for that. Quadcopters, I'm sure some of these images are taken from a quadcopter. And then we've used the twin otter, for example, and I think NRL is running that now. Luc is going to talk about another aircraft during his talk. All right, really interesting aircraft deployment. So the other thing, of course, Argo is amazing. I think it's a community effort, right, to keep all of these floats out in the ocean. This is, I think, these Argo by the numbers, I think they're fairly recent, because Scripps has said there's now 3,941 floats as of a couple of days ago in the ocean. You can deploy these several ways, just by hand over the side of the ship if you're in the region of interest, because you have to kind of redistribute these occasionally. This is Steve Jane from Woods Hole. He deploys these from aircraft in front of hurricanes, say. All right, and so this is the equivalent would be our Raywin sound. Now, you'll notice that it's a little sparse over the ocean. So what do we do about that? We have to come up with better ways of making these measurements. I'm going to go through this fairly quickly. This is butterfly. There are people in this room that know a lot about butterfly, if you'd like to talk to them more. But it is basically, it's for us. It's for the air-sea interaction community. And it's meant to get profiles of temperature and humidity out over the ocean so that we could get fluxes. And so we'd have global coverage from this. We have fixed platforms that I've used in the past. The FLIP, the RACIX tower, and the ESIT at NVCO, that's the Air Sea Interaction Tower at the Martha's Vineyard Coastal Observatory. That's Martha's Vineyard back there. Moving forward. So how can we go higher? Because those end at about 25 meters, those towers, okay? It's high enough for some studies, but not high enough for many. So what we're now working on is these LiDARs. And so this one was being validated next to the Air Sea Interaction Tower. And we're using this data to do things like this. So the symbols are from the LiDAR themselves, and the lines are from the core algorithm. You can see the core works fairly well in convective conditions and not so well in stable, right? And we run WRF along with this, and similar results. WRF does a little better with the low-level jet, I would say. Now, can we go even higher? And this is where we're relying on the wind energy community. So, for example, the answer is yes, and I'm going to focus on the this gravity-based approach with just a big cement ball here. You can see people here. This thing's enormous. It would fill this room. And so this is just an artist's conceptual drawing. And I wanted you to note, that's why I put this arrow here. This is how tall the Air Sea Interaction Tower is relative to this thing. We can do this as a community. We would probably need an elevator in here, and these are walkways for us to maintain the instrumentation. So these sorts of things are possible. The cool thing about the cement is that it'll drive artificial reefs very easily. So, and you can see how happy the whale is that it's there. All right. All right. So, and this leads us to super sites. At some point, we're going to have floating platforms so we can set these things up just about anywhere on the planet. Last thing is just, if I could have a few more minutes, so this is what we are setting up for a DOE project for the wind farm that's offshore of Martha's Vineyard on our continental shelf. So many of the assets, many of the assets I've already talked about are here, the Air Sea Interaction Tower. The idea was to put a large barge out in the center of this is the lease area for the wind farm, and sort of mimic what we're doing at ACIT, but in deeper water. Wouldn't it be great if we could put one of those gravity-fed things right in the middle of that? We'd have an ocean test bed right there. Just a couple more slides, and this is where I'm going to shamelessly promote the WHOI. This is the Coastal Endurance Array off the Oregon-Washington shelf. There's a line off of Washington of buoys. There's one off of Oregon. Some of these are connected to the cable that goes offshore, so they're coming straight into Pacific City. And this is, you can see the glider pass in here. And people are numerical modelers are starting to use this data set as they figure out how to use glider data in particular to validate their models. I'm talking briefly, the Pioneer Array was up on the Mid-Atlantic shelf. It's being moved down to the Mid-Atlantic Bight. It's going to look something like this. There's going to be an array of buoys, and then this box will be for the gliders. They'll extend up north that far. Last slide, I swear. So imagine that we have this sort of array running for 5 years for free. Anyone can use it. And let's add, a transect from one of these many vehicles that we have now. There's your mesoscale array. There's all sorts of interesting things with the Gulf Stream meanders occasionally coming up onto the shelf here, fresh water out of the Chesapeake. So that's my thought. So thank you, everyone. So everyone, I'm going to go.
Thank you very much, Jim. You can sit up here and join me, and we'll take questions at the end. So next we'll welcome Luc Lenain from Scripps Institution of Oceanography. And while he's making his way up, I will just mention that the butterfly mission that was mentioned by Jim, we've got a presentation on that tomorrow morning, so everyone can look forward to that. I'll keep it here, thanks. So over to you, thank you.
All right, thank you. So today I'll be talking about airborne observation of surface wind, wave, and current from meso to submesoscale. I mean, make sure that it works. And actually, I ended up Works. Yeah, I changed my talk based on some discussion we've had the last few days. It's now collocated and coincident airborne observation of surface wind, wave, and current from meso to mesoscale. I obviously need to acknowledge my co-author. This is a big team effort, actually with collaboration from a team in Norway, from NTNU, developing some of these new tools. We have a publication under review presenting some of the technology and that I'll be talking about today, and I'd be happy to send you a preprint if you're interested. All right. There was a lot of discussion over the last few days on which scales are important when it comes to air-sea interaction, and I wanted to start my talk to remind ourselves of the scales that we're dealing with, and that's really the challenge. Everybody is going to come with a preconceived idea of where we should focus on based on their own expertise and experience, and people from mesoscale field. I come from very small scale initially, and I've been slowly getting into larger scale. But the reality is, we need, when you want to, in developing better understanding of the coupling between the ocean and the atmosphere, we need to understand effectively all those scales of air-sea interaction. So I wanted to highlight this here because this is really important. You cannot ignore any of those. If you're interested in mesoscale air-sea interaction, you have to worry about the small scales as well. So that's our challenge as observationalists. How do we do this? Because you have to get those phase resolve observation over a broad range of scales. An example that I wanted to highlight, for people in the audience that might not be familiar with this, this is a picture that was taken at a front in the Gulf Stream, where we have warm water on one side, cold water on the other side. Let me see if I have, oh yeah, there you go. So warm water here, cold water here, and there is this very sharp front. Things are sharp when you start observing some mesoscale features in the ocean. And what you're seeing is on one side you have breaking, enhanced breaking, and on the other side you have no breaking over a large area, as you can tell from the field of view of the camera or of the image. The thing to keep in mind here is that the waves here are not wind generated. It's not like if you have excess wind on one side and less wind on the other side. It is associated with wave current interaction. So this is really important if you think of this in the context of scatterometry, for example, that is going to collect information of the wind from the roughness of the surface. So today I'm going to be presenting coincident and collocated observation of SST, surface currents, wind, and property of surface wave across some mesoscale using this instrument package that we've been developing at Scripps at the RC lab for the last 10, 12 years now. Because those observations, as was reiterated a number of times over the last couple of days, those coincident collocated observations are crucial to develop better understanding of the physics of the submesoscale and in turn, enable parameterization for model. I don't have enough time. There's too much to talk about, but fortunately there is a number of talks, a number of posters / talks that really expand on some of the things that I'll be talking about. In particular, Nick Pizzo will be talking about strongly modulated surface wave at the submesoscale front. This is enhanced breaking, and Mara Freilich will be expanding on some of the surface currents observation and velocity gradients observation that we've collected from some of our instruments, and Bia will be talking about some of the waves observation. So talking about observation, what we have developed over the last 10, 12 years at Scripps is called the MASS, stands for Modular Aerial Sensing System. It's an instrument package where we try to collect observation of SST through infrared camera. We use LiDAR. This is a 3D point cloud of surface wave around a buoy in the Gulf of Mexico. We have high resolution video, hyperspectral camera, GPS IMU, and a new instrument called DovViz that I'll be spending a little bit of time on. And the key here is, in terms of variable, we want to have collocated coincident observation of surface wave, directional wave properties, in SST for the ocean surface process, video as well. And with this new instrument that I'll talk about, we're actually able to get high resolution spatial observation of surface current. How does it work? The obvious is really simple. It is really primarily a camera, pointing forward of the aircraft track. So we can have, and we can observe the same spot of the ocean for a long period of time. If you have multiple images over time, collected from the aircraft, if you target on one spot, you're going to have effectively a drawn downward-looking like movies of the ocean surface. And this is an example of how it looks like. I had an aircraft for just to locate the, where we were at, but obviously we're not taking a picture of ourselves. But this is the kind of information you have. So this is at twice the speed of data collection. So you can see a lot of detail. You can see wave breakings, and you can see those waves propagating. It might be hard to see on the screen. So a lot of information here. In terms of wave breaking, you can track those waves. This is, work with the student where we track those waves as a function of time from onset of breaking all the way to annihilation effectively. And one thing that I'm excited about and relates to Nick's poster, you can also start zooming in on those front where you see enhanced breaking. This is a 50 seconds video from the NASA S-mode IOP that was just completed. So a lot of information on the surface kinematic. So how do we quantify the surface current? So if you take one of those little square that I just showed, this is taken, again, this movie on the left is taken from an aircraft going at 180 kilometers per hour, but very well georeferenced. So you take this cube of data in space and time, you do a 3D spectrum, and because of the well-known dispersion relationship, all the energy is going to fall along this dispersion relationship. The dispersion relationship is modulated by the current as a function of frequency, depths, if you'd like, and in turn you can invert for the upper ocean currents and shear over the penetration depths of the range of waves that you're sampling. So this is an example here of what we get for one case. This is depth profile from Doves as a function. So this is roughly from 30 centimeter water depths to 2.5 meter water depths in one instance. Everybody's asking me, how well does it compare to ADCPs? So we have those wave gliders that Jim mentioned that are equipped with, that are well motion compensated. So we were actually able to validate those observations. I will mention that Doves measures a Lagrangian current, which means that it includes the Stokes drift, but we do have wave measurements to compute the Stokes drift as well. But that's a longer story. Anyway, so this is 1 point measurements. Now, if you average, if you take a depth average of this profile and you look at it as a function of space along the track of the aircraft, and you plot it on top of SSTs that you get from the other instrument, this is the kind of things that you get. And in that case, I used 2 different depths. So you see this very nice coherence of those features. This was taken during S mode. Very high resolution. This is 1 kilometer here. And we go to even higher resolution. This is another experiment across the loop current, across 2 eddies of Southern California. We had a flight track that was trying to target those 2 eddies. The background velocity vector is from HICOM, and as well as the SSH that you see in the background from HICOM. I'm showing a 1 kilometer long track average surface current along those track. And generally speaking, you see good agreement at, for the lower scale, which makes sense. We expect that from ICOM, but they're missing, the smaller scale, the submesoscale is not well represented with ICOM. So if you go to higher resolution, so this is the same track here, and if you zoom in on this area, right over here, where a lot of things happen, this is what you get. So you get, this is an example here where you have strong submesoscale variability. We have the SST that tells us information about the surface properties. There is a clear front that corresponds to some rapid change in the surface currents. So it all makes sense. You can look at different variables. Again, having all those different fields together, we can measure surface wind, looking at the properties of the LiDAR return that we get from the topographic LiDAR. And there is some work that we did with Ken Melville several years ago. So we're starting to really combine all those crucial information. So just taking the spatial variability of the currents, you have those long transects, you can start doing spectra. So we, I don't know if you're familiar with this work, but Terry Chereskin had looked at the kinetic energy spectrum in the California current, trying to characterize the transition from balanced to unbalanced motion. So she used sheep observation and model, and she was getting down to, maybe 20 kilometers kind of scales. With Dopplers, with kilometer scales, you can start, extending some of those observations and start looking at this transition from balanced to unbalanced motion. And this is some work that Mara is talking about in her poster. We have a lot of things we can do, but I'll just skim through this very quickly for the sake of time. Not only you can get cross-track, a long-track average, but you can get swaths of surface velocity. This is an example here at 128 meters along horizontal resolution. So if you're a modeler and you see a surface, a map of surface velocity, right away you're seeing gradients, velocity gradients. You think about divergence and vorticity, looking at joint PDF, and this is again some of the work that we're exploring in trying to identify what are the processes that are really driving the submesoscale. We can look with those kind of observation. Now that we have the current, we have the wave, we can look at the modulation of surface wave at different scales, both small scales, where that's going to be related to some of the things that I showed, for example, with the front, where you see enhanced braking, very intense modulation of the shortest wave, but you also have modulation of the wave fields through refraction with larger scale kind of current field that you would experience in this. And, that's really the nice, the motivation behind developing those instruments is trying to, in great part, to cover this very broad range of scales, spatial scales, going, like these are kind of like mesoscale, bulk estimate of the wave field, all the way down to, spectral information that gives you the directional distribution of the wave field down to some meter scales. And that pretty much conclude my talk. I'll leave this here. The message here that I wanted to convey is that we need those observations. We're at a point where we need coincident, collocated observation of all those fields over a broad range of scales. And this is just one instrument. There's also Doppler scat that is trying to develop this kind of technology, and combining it with in situ observation, I think will enable quite a bit of developing better understanding of the physics of Earth interaction. Thank you.
Thank you very much for another excellent talk. So now we're moving over to a virtual presenter. We have Samantha Wills from the University of Washington and NOAA PMEL. So hopefully she is online and we will see her slides soon. And just a reminder, anyone who is virtual, feel free to write any questions in the chat at any time and we'll come to those at the end of the talks. So Samantha, if you're there.
I was waiting on Kelvin. I was supposed to try to access this through the thing here. Okay, and is it possible for me to see the slides, or I'm not able to see these slides?
I think we're just working on it. We can hear you at the moment, and hopefully.
Oh, wonderful. Okay, I see the slides now, and you can hear me
over
okay?
to you. Yeah, that's perfect. Thank you, Samantha.
Awesome, and hopefully I am able to go forward. I'll let you know. All right, I'm Samantha Wills. I am an early career scientist, about 1 year past my postdoc, working with Megan Cronin and Dongjiao Zhang, and we've been using sail drone uncrewed surface vehicles to look at, I think as Jim said, the wimpier part of the ocean in the tropics, looking at the tropical Pacific, and so I'm here to present a little bit of how that research might benefit the observing network. Let's see. Okay, so if you could go forward for me, it looks like that'll be the best. Thank you. So you've heard about sail drone a little bit throughout this workshop. So here's just a brief schematic showing you sort of the distribution of these atmospheric, oceanic, and biogeochemical sensors that are outfitted throughout the drone for those co-located measurements that you can get. And a few important things here is that the data we receive is near real-time telemetered 1 minute mean and standard deviation data. So we're really getting this great real-time high resolution snapshot of the ocean, and that these drones are powered by wind energy and solar energy and are rather, so that's a kind of a green footprint for collecting observations, which I believe is important. But also they're remotely piloted in the sense that we have a measure of navigational control of these drones, and we're able to sort of help the pilots guide them to where we would like to sample within the ocean, and I think that that's rather exciting. Next slide, please. And so for the sake of the mesoscale variability and submesoscale, I'll be focusing on atmospheric cold pools that we've observed. And if you're not familiar, cold pools are essentially those cold air downdrafts that occur underneath precipitating thunderstorms. And for the tropics especially, they're thought to be important for triggering and organizing convective activity on the larger scale. And over the land, typically we're able to do, look at these things through weather stations, radar, radiosondes, but as we all know, over the ocean, we are very limited in the amount of platforms that we have to even try to resolve these scales of air-sea variability associated with cold pools. Next slide, please. So starting off, this is a case study we performed in our 2019 mission to the Eastern Tropical Pacific. And what we have here are 3 just different domains of the same snapshot in time, showing the 4 drones that we had positioned around the 9 North 140 West Tau mooring of the Tropical Atmosphere Ocean Array. And we were able to capture a cold pool event that was propagating through this domain within a 2.5-hour period. And what we can see here is how we're able to get at sort of the subgrid and subpixel variability with respect to these satellite and reanalysis products. The iMerge data was actually quite helpful because we unfortunately cannot measure rain. So we do not have that information to know if there was a parent convection associated. So that kind of gives us some supporting information. But the other field is showing the 10-meter U and V winds of 1 hour sampling from the ERA 5 data. And we can see that, as mentioned earlier, there is a difficulty, it seems, in capturing the smaller scale, rapidly varying phenomena that's not shown in the background wind fields. Next slide. And so to look in at the 1 degree domain here, we see that we had just a sort of a density of sampling with these 5 different points here between the 4 drones and the Tau mooring. And you really can get a sense from just having this sort of spatio-temporal sampling in the sense that you can understand the direction of the propagation. We can see in the time series here in this air temperature one, panel D, shows you that the cold pool front first impacted, drone 1069 in the southeast corner of that box, and and makes its way towards the northwest, which you can see simultaneously in the time series. And importantly, you can also see how as it's propagating through the domain, as it reaches each platform, we can see that the temperature drop is beginning to weaken. We can see that perhaps we're capturing the beginning of this transition to its recovery phase. And then one last thing I'll point out here in the bottom right panel, you can see, of course, that these cold pool events are associated with gust fronts that follow immediately behind the leading edge and increase the winds. And especially when you look at the sign of the wind, that will come into play a little bit later on. So next slide, please. So coming from an atmospheric meteorology background originally, I kind of got thinking about what we do over land, such as, for example, the Oklahoma mesonet, and how it's just this density of weather stations placed throughout the counties within Oklahoma that's able to resolve, perhaps like Brock et al. Shows here, this mesoscale low pressure field. And so I kind of got to thinking, well, how could we use our new technology to do what we do over land in a, a fraction perhaps, but still better than nothing over the ocean? And what if we could use these drones that take these co-located measurements and high resolution timescales to be creating perhaps these adaptive mesonets that we can send out into the ocean? And what I have shown here is the spacing of the tropical atmosphere ocean moorings in the white squares, and how many Oklahomas you could fit in between the meridional and zonal spacing of those of the buoys, which are really important long-term historical time series that we must maintain. But how can we get at the information in between? And I see a lot of potential in using these drones in both the spatial and temporal timescales, measuring simultaneously to get at these, more mesoscale and submesoscale type of systems. Next slide, please. And so to scale this out into the entirety of these arrays, such as like I mentioned, the Tau array and also the Parada array in the tropical Atlantic, this sort of gives you an even better sense of that state of Oklahoma and how what we're talking about trying to observe is so just small relative to the vast size of the ocean, but so important for capturing these things that, if we could have, 4+ drones sailing in formation, being able to kind of create little mini grids within that type of information that we could get. But next slide. That might be a little pricey, 4+ drones going year round. And so one thing that's being discussed is similar to how the Go Ship program works. What if we could have Go USV lines where we have at least 2 drones sailing repeat transects within key critical regions of like the tropical Pacific, tropical Atlantic, anywhere in the ocean really, and being able to do these hydrographic surveys to collect all of these different variables and measurements to at least perhaps work towards parameterizing certain regimes like the ITCZ, the cold tongue, anything in the mid-latitudes and up, being able to just sort of break them into little parameterized quadrants, and also coupling the uncrewed systems with existing ship measurements and Tau buoys and other buoys that are out there to really just, I think, get at that increased sampling density of observations over these data sparse ocean regions. Next, please. And so kind of not so much a proof of concept, but in a sense, at least in this pilot study that was performed with 3 missions between 2017 to 2019, and then the ones we've had since, we have done these trajectory type missions where you're sailing along a space-time continuum and collecting these observations. And one of the questions is, how can we make these observations useful to people or useful for assimilating? And one way that we've been able to use these high-res time series in the air temperature, for example, was to look at drastic changes in temperature that were likely related to atmospheric cold pool events. And this is a very conservative estimate given that I don't have the rain data. So this was identifying about 276 cold pool events for the statistics that'll be shown on the next slide, if you could please proceed. And so one thing I'm very interested in understanding is how do atmospheric cold pool events, influence the local air-sea heat fluxes? And so looking at the bulk formulas, the key terms here are your relative wind speeds and then your air-sea moisture and temperature gradients. And if you look at the top right panel, this is showing you the air-sea temperature gradient anomalies relative to the preconditions before the cold pool front hits at lag 0. And we can see in the gray line, which might be hard to see, the gray line represents the 1-minute mean data, whereas the black line shows 10-minute average data of the same data. And we can see that even that change in temporal resolution has an effect on your ensemble results, where you can see that the timing is a little bit muddied throughout that period because these events happen so quickly, these fronts, these passages, that they're not going to happen at 10 minutes on the hour. And so as you try to get your bulk, ensemble statistics, you're going to be limited a bit by your temporal resolution and, how that might affect the overall fluxes that you calculate. And importantly, too, you can see that relative to the timing of the temperature front, we see that the wind speeds increase immediately behind it. But depending on your resolution, again, that could happen anywhere between 5 to 10 minutes. And especially in both the humidity field and the wind field, we see the change in the amplitude of the peak of about half when you go to the 10 minutes. And so that's what's been really interesting to see, just how rapidly these variables are changing. But so given the wind, we were interested for the next slide, please. And looking at the core algorithm, as Jim was mentioning, worked on by Chris Farrell and Jim Edson, and is particularly interested in that gustiness parameter that's intended to account for this missing wind speed variance that occurs when you have an average. So for example, you have a 30-minute wind from the east and a 30-minute wind from the west of the same amplitude. That would suggest you have 0 wind if you took that average, but that's not true. So the core algorithm already does implement this gustiness parameter, which essentially relates the square of your scalar wind to the square of your vector wind. By taking that difference, that would be the gustiness that's being unaccounted for in that average. But one of the, I think, drawbacks for now is that this gustiness parameter has mainly been derived for low wind regimes during fair weather conditions. And so we don't have a great understanding and a lack of direct observations to know how well these bulk estimates are working. But we were able to actually calculate from the Saildrone high-res data the missing variance during hours in which cold pools did or did not occur. So if you could please go to the next slide. So this is just, again, to reiterate with the scalar wind, we're talking about taking 1-minute wind speed measurements and averaging them versus taking hourly average zonal and meridional winds and averaging that for the same time period. Next slide. So this is a little messy, but what's being shown here essentially is for a single drone throughout the entire time series, except that I have plotted latitude instead of time on the x-axis. And this is showing you can see sort of the regimes we were within between the ITCZ and the cold tongue, and how in regions where you're in the ITCZ, there's a lot of these missing wind speed variance. So what's being shown in the black is what we calculated directly from our Saildrone measurements for within an hour time range. And all of these pink dots are representative of a cold pool event that was happening during that hour based on our criteria. And we can see that star here from that case study I first showed you, we have a missing wind speed variance of almost 12 meters squared per second squared that is not being accounted for in the vector winds. And then the light blue line is actually showing you what the core algorithm output, the gustiness squared, is what's being plotted there. And you can see that that little blue line is nowhere near the magnitude of some of those large spikes from the observations. But then looking at the bottom panel, we repeat this except for 10-minute average data. And we can already see marked improvement when you have that better temporal resolution and there's less room for all that variability to get in. And our star actually goes down to almost 0 and much better agreement with the core algorithm. And you can even see in the cold tongue how much better it performs, since that's a lot less convectively active. Next slide. And so to put this in the context of the heat fluxes, one thing that we were able to do is, granted we're using the bulk formulas as are, but we are taking the differences between if you fed it 10-minute average input versus if you fed it 1-hour average input, and then calculated what that hourly output would be between the two different inputs. So it's showing you an hourly average difference based on 2 different temporal inputs. And so this would suggest that when you have the coarser temporal averages, you're underestimating, especially during these cold pool convectively active conditions, you're underestimating both your sensible and latent heat fluxes, anywhere between 10 watts per meter squared for the sensible and up to almost 40 for the latent, depending on the conditions. And so, there's ways I think we can use this data to work on parameterizing parts of these bulk flux algorithms in order to improve our ability to sort of, estimate what's happening not being accounted for in one regime versus the other. And so if you go to my last slide, please. And so just kind of summarizing here with some challenges and opportunities, I think the biggest one is being able to validate these findings from previous modeling experiments and satellite measurements. Measuring beyond the near surface, sail drones are limited to the air-sea interface. Being able to compare bulk flux estimates to direct observations and understanding how should we take these measurements in ways that will be helpful to the operational forecast models. And so I just want to put in a plug for Megan Cronin's UN Decade program OASIS, Observing Air-Sea Interaction Strategy. That's something that's working to bring international collaboration on our global observing system, as well as a potential NOAA Climate Variability and Predictability Program field campaign for intense observing within like the Pacific upwelling and mixing physics regimes and eastern edge of the warm pool. And perhaps there's room for this community, which I have only which I used to be a part of, the mid-latitudes from my grad school, to now the tropics, but perhaps, we can merge together and really work towards common goals. Thank you.
Thank you so much, Samantha, for another excellent talk. We'll be inviting you back in 15 minutes or so for the panel discussion. So before that discussion, we have our final speaker, Joseph Tadezio from NRL. Over to you. Thank you.
Thank you so much for having me. I know it's the last talk of the day, so I'll try to keep it fun and interesting. We're going to cover observations and modeling and state estimation, so this is going to be fun. So the background for this, the impetus for the project is actually state estimation. So kind of a vogue topic in ocean data assimilation right now is this multi-scale data assimilation. So a number of different agencies have actually implemented this and found it to be quite robust and helpful when you have patchy, high-resolution data within the context of very coarse, limited, regular data in the background. So I've got an example of what these updates to the model look like for each of the steps. So you'd usually do 2 sequential data assimilation steps, starting with the large scale, which is the top left, and you can see kind of larger blobs here for the larger scale features being corrected by things like the nadir altimeters. And in the middle, I have the small scale correction, and you can still see some of the nadir altimeters, but you also hopefully will see these simulated SWAT tracks where you're making those smaller scale corrections along the highly dense swaths of the altimeter or the Karen altimeter. And then the final update is the summation of these 2 fields. So you get a combination of the large scale effects where there is no small scale data, and then also large and small scale information where there is both combined together. So we've found as a community that this is very robust for correcting the horizontal scales. One thing it's lacking is that as it goes from one scale to the other, typically the vertical physics that are assigned to each of those scales is exactly the same. And that's wrong. We've seen a lot of talks here and many other conferences where as you start moving down from mesoscale to small mesoscale to submesoscale, those vertical physics change. I think one plot that stood out to me today was you had the wavelength on the x-axis and you had variance plotted. And as you went down in wavelength, you saw this kind of rise in the variance up towards into the mixed layer. So this is kind of a deficiency in the multiscaler we're trying to correct. So with some modeling results in the past, we've calculated these vertical covariances. So these are these depth covariances. And if you run some filters over it, you can get the large and small scale, and you can see that the small scale is more shifted towards the surface and it has smaller off diagonal elements. So it's shifted towards the surface and it has smaller correlations with depth as compared to the large scale. The problem is these are with models, so we don't really have good estimates of what these should look like with observations. So the whole point of this project is to try to do that with some high resolution observations from the S-mode experiment. So the first thing we're going to do is talk about adaptive sampling, because to get the high resolution data that we need, we're going to actually have to put some instruments out and collect the data. So for everybody online, I'm going to start with the 10 glider pictures, and I'm going to rotate clockwise around to show this kind of feedback loop for the S-mode. And if you don't know, that's NASA's experiment, the submesoscale ocean dynamics experiment that's done 2 campaigns off San Francisco Bay over the last 2 years. And NRO was tasked with NAVO or the Navy put out these 10 gliders, and our team was tasked with coming up with a sampling strategy for what the gliders should actually do when they're out in the water. And since this science, instead of just grabbing something off the shelf, we had to do something cool and exciting new to write a paper about. So this is our sampling strategy here. So we put the gliders in the water. They collected the TNS profiles just like any other glider does. And we actually assimilated those temperature and salinity profiles into our 1 kilometer model. And you can see it's off the bay here where the S-mode region was. Now, besides just an update to the model to get a better initial condition for the forthcoming forecast, our system actually produces this field called forecast error. And there's a lot of fancy math behind it, but essentially just the layman explanation is that the red areas are places that have not been sampled recently by the observations. And the blue, green, yellow areas have been recently sampled by the observations. So our sampling strategy was to synthesize with the model such that we send the gliders where the model has not been updated recently. So if you just use this field here, actually your gliders would be incentivized to go off to the west where the really red areas are. So we applied a localizer around the S-mode polygon, and we came up with a reward function that looks like this. So this reward function says it does a very complex set of algorithms on a supercomputer, and it says the glider should go to where the reddest spot is, and I should also stay away from other gliders. So the sampling strategy is to go where the model has not been recently sampled by real world and stay away from each other. And then the decision loop starts all over again. So they go out and collect more profiles. They go to a new place. Those profiles are assimilated, and the forecast error is reduced where they just took a new observation, and they're incentivized to go away to a different spot. And so I'll show you what that looks like in real time here. So again, red is go here, blue is stay away. So we want to stay in this region. So when we first deployed them, we just used a basic Gaussian function to get them in the region. And then you can see at some point we turned on the adaptive sampling technique, and the gliders are going around like little Pac-Men eating up the forecast area. Oh, excuse me. And when they make a hole, eventually the forecast hour reinflates itself, and then they're incentivized to go back where they sampled like 10 days ago. And so they're not just sitting in one spot collecting data at that one location. They're going around the domain and adaptively sampling based on what the model is doing. Okay, so that's the first part of the talk. Now we sent these gliders out, we adaptively sampled the region, and now we have some data for us to come up with these covariances, these scale-dependent covariances that we started the project looking for. So in the top left corner, I've got a picture of all the samples that were taken during the S-mode campaign. You see we did a pretty good job of staying around the S-mode box. And what I have plotted up here in the top right in this A panel is all from one of the gliders, all the samples that it took. So each of these little blue lines is a V set of diving and coming back up to the surface. Now to do a scale decomposition of this data, we can't have gaps. We want to run an FFT over it. So we did a little interpolation function to fill in the missing spaces. And for our analysis, we started at, actually what we did was, excuse me, let me back up a second. We remapped this from time to space. So we know what the lat-lon reporting of the glider is, so we can calculate the distance between each of the profiles. And so we can put this on distance instead of time, which is probably how you're used to seeing the glider data. And we do the interpolation function, and if we run an FFT over this, we can do a spatial-based decomposition of the data instead of a temporal decomposition. And so that's what this looks like here in the top left corner. So I picked 200 meters out. We run the FFT over 200 meter depth level for this panel up here in B. And we also we sampled the model at the same location as where the observations were taken. So that's what the black and blue lines are in the spectrum here to the left. The other thing we calculated was the error between the two. So we took the model minus the observations, and we also took the spectrum of that. You may notice that the red line, which is the error, has less variance in power spectral density space than the model and the glider. And that's because the model at larger scales actually has skill. So when you subtract the two, those features are eliminated and the variance of the subsequent field goes down. At some point, you get this crossover effect where the variance actually goes up for the error because now you have no skill from the model and you're just doing a simple summation of the variance from the two fields. And so because we're looking for the covariance for the large scale multi-scale step and the small scale, we defined our boundary as the crossover point where the model has skill and where it does not. And so if I plot this in 2 dimensions, so all depths, and use this value, normalized value of 1 where this crossover value is, I can get an estimate of what the constrained scale of the model is. What's the horizontal scales that the model has skill up to? And it turns out that value is about 250 kilometers for this experiment. So what we did was we took this B panel that was the interpolated and we filtered it to 250 kilometers. And then now we can calculate our covariances. So on the left-hand panel, we have the large scale from the observations and from the model. And on the right-hand panel, we have the small scale from the observations and the model. And I don't have time to get into all the little nuances of the differences, but hopefully you can see at least qualitatively that they are different between the small and the large scale. And fortunately, they're actually pretty similar between the model and the observations. So our application here is, if we want to go back to the multi-scale 3D VAR, now we have some qualitative estimates of what those observation-based vertical correlations should look like so that we can get the physics right in the second step of the multi-scale. And then also a big problem is we don't have many of these high resolution observations. This was kind of a unique data set. So if this data suggests that if the observations aren't available, you can use the model in its place. So the last thing we're going to do is a step forward in state estimation. So Greg Jacobs, my postdoc advisor, likes to talk about this moving of the wall concept. So here I have a spectrum for a number of different variables from the ocean. And like we talked about before, the model has some skill in some set of larger wavelengths. And at some point, it is unconstrained by the observations. It doesn't have information from the coarse observations. So the model does not have skill in this region. And at some point, the model just produces mostly unrepresented features by the physics. So in this case, this is a 1 kilometer model. So we usually multiply it by 8 to 10 grid points. And the model doesn't really represent the physics. So our challenge here is to always push the boundary of this green and yellow to the right. So how do we get more skill in the model with either the same observations or new observational data sets? We've seen this effect with the multi-scale where we're able to improve the skill of the assimilation by going from multi-scale instead of single scale. But the problem is not only do we not have those congruent physics problems going on, we also have a problem that you have to do 2 sequential analyses. So it's double the computational cost to do a multi-scale. So one of the tricks that we tried to pull here is, can you do a multi-scale like assimilation with only 1 analysis step? And that's our hypothesis here. And the little trick that we pulled to do that was by adjusting the assimilation scales, the horizontal assimilation scales, only within the presence of the high resolution glider data. So away from the S mode region, we kept the scales still large because out here, all you're getting is things from the NADAR, altimeter, and Argo and SST, which is fairly coarse. But within the center of the S mode box where we had all those gliders running around, we reduced the scales of the assimilation. And I give you a little cut through here in 1D. And so hopefully you can see that they shrink within the S mode region and then they come back up outside. So we're not destroying skill away from the S mode region, but we're trying to improve it within the S mode region. And so the effect is here. There's 2 effects, one on each side. So I'm going to talk about the left side first. So our algorithm actually only allows you to assimilate one observation per decorrelation length scale. So by reducing the decorrelation length scale in the assimilation, you actually assimilate more glider profiles. So at some point in the very beginning here, you can see you just have a little bit scattered set of profiles. And on the 10th, we turn the adaptive assimilation on, and hopefully you can see that there's many more profiles assimilated because of those shrinking correlations within the S-mode box. The other effect is we make smaller scale increments. So if you remember back on the first slide, we had those small scale increments from the second step of the multi-scale. The top is a parallel experiment that just had a constant correlation scales all over the domain, so a single scale but had constant over. And then the bottom panel is the adaptive assimilation. So hopefully you can see that away from the S-mode region, the increments are pretty similar, the update to the model to make it more accurate. But then within the S-mode region, we actually have these smaller corrections, these smaller scale corrections provided by the high resolution glider data. And so we can go back and we can do our scale decomposition like we did for the first part. Thank you very much. Yes, I'm finishing up. And so for the constrained scales of the simulation that use the same assimilation scales everywhere, you get that 250 kilometer effect. But when you change the adaptive to the adaptive simulation, you actually move the scale down to about 100 kilometers. So that's a pretty big improvement. And just so you don't think we're cheating, the last panel was evaluated at the glider locations that we actually assimilated. So we probably should have some skill. So S-mode actually had a ship that went out and took CDD gas that we did not assimilate. And just to briefly say, the black line is the simulation that had the same scales everywhere. And the dashed black line, which is doing better on an RMS temperature perspective with the adaptive assimilation. So there's a control set for you. Okay, so just to finish up, we talked about the adaptive sampling within the S-mode region. We showed the large and small scale correlations based on observation data for the first time. And then we implemented a unique assimilation technique that allowed us to assimilate more glider profiles and improve the skill of the assimilation using only one assimilation step instead of two sequential ones that's done in the multi-scale. Okay, thank you, that's it.
Great, thank you so much, Joseph, for an excellent talk, and to all of our speakers. We now have time for discussions. So if anyone has any questions, please come up to one of the microphones and we can ask any of our panelists here. We also have Samantha, who's still joining us in the WebEx. Great, Thomas, over to you.
Okay, here we go. Yes, thanks. It was a very interesting session. I have a question for the last talk. So in the atmosphere, well, you have all these observations, that's great, but sometimes you want to put them at specific locations where they get the biggest bang for the buck. So I was just wondering, so you focus very much on 3D WHOI, but have there been also things happening in the ocean where you kind of look at tangent linear models or other methods where you identify locations where you should send them to get the best improvement?
Right, you can do adjoint sensitivity, and you can try to figure out where either in the past and the future where you should sample to give you the best bang for your buck. At NRL, we've talked about that, and there's been some kind of primordial implementations, but it's not as far along as we'd like. So, but yes, that's definitely a direction that we're thinking. That's a great idea.
Yuri from UMass Dartmouth. My question is to Luc Lenain. And I'd like to have a sense about the next steps for WHOI in terms of what are you planning to do next and what kind of applications and enhancement that you do for Airborne, WHOI and other applications.
Okay. Well, let's try this. Okay. In terms of, the next step for us is really start going through all the observations we have been collecting, because these are quite unique. And I'm not planning for any new technology development. We have a very robust system. We're just collecting a lot of those observations, co-located with other in situ assets. I mean, S-mode has been mentioned numerous times during the meetings. We have an experiment, IOP2 starting in a few weeks. So that's really our focus. Operationally, what I'm really intrigued is how high I can go, because then I'm going to really start increasing my spatial coverage. I don't go too high usually, so my swaths are up to, let's say, 1.5 to 2 kilometer wide for the ocean currents with a 250, 120, whatever spatial resolution. I go fairly low, which is a challenge in the processing of the data, to have the collocated wave data. And one of the things that I forgot to mention is not only the LiDAR give you information about the directional property of surface wave, but it also gives you sea surface height. So you can get sea surface height anomalies. So effectively, you can start trying to identify the ageostrophic component, along those tracks, especially when you have like a 280 system like this.
And a follow-up question. So is that possible to put the same instrument in commercial ships and use that to measure currents?
In principle, yes. And we've done it. I should mention that the principle is not new. A lot of other groups have been using, the dispersion relationship to infer current for a number of years. I did this 10 years ago with Peter with X-band radars. You can do that. Other groups use it from drones, for example. I think the novelty here is that it enables to give you a snapshot, instantaneous snapshot of the spatial variability of the current. And it's really important when you start trying to understand the physics of some mesoscales, because you can't really do that from a ship. A ship is too slow, and there will be a aliasing issue with the spatial variability of the features that you're after.
I'm Sikarai from University of Rochester, PhD student. My question is to the last speaker. So I really like the idea of the yellow arrow pushing towards high wave number. And I found that the adaptive assimilation very witty and very clever. I have a curiosity on when you try to push that yellow arrow towards high wave number, is it more appropriate to push it in the Fourier space or in the physical space? Because if we do it in the Fourier space, then we'll lose a locality in the physical space. But if we do choose to do that in the physical space, then the Fourier space is, again, different, right? So, or should we do some kind of in between?
Yeah, that's a great point. I should have been more clear. So we do it in the physical space, and then we use the Fourier space as a metric. So that was after the fact, going back and looking based on the update in the physical space, how well we did in the Fourier space. So I think with the arrow thing, I think the most important thing is because all the variance in the ocean is shifted towards smaller wave numbers, you have to always nail the large scale first and then move down, because you're always getting your biggest bang for your buck by getting the large scale features in the right place. So I think that's what's really nice about the multi-scale too is, if you could add more steps, you just need to sequentially go down scale until you've mastered each one. And so that's in the future, that's going to be a balancing effort, because you've got some instrumentation that may allow us to do that, like SWAT. And you have to have a comparable data assimilation method that can treat the data in the way it needs to be treated. Does that make sense?
Yeah. Thank you so much.
Thank you.
I didn't introduce myself the first time, so I'm Thomas Spengler of University of Bergen. I have a question maybe for all of you, but maybe the first couple of talks in particular, and it's a lot about focus about new instrumentation and what we as a research community want to put out in the ocean and stuff. But I'm also wondering about platforms of opportunity. So I mean, for example, sort of Europe, where I'm from, so then there's all these wind parks, and of course wind parks have a problem from the atmosphere because you have a downstream effect. But you know, there's a lot of these windmills, so you can just always make sure you use only the data from the one that's facing the wind. But I'm wondering, have people thought about putting stuff on the ocean on these kind of platforms? And then, of course, follow up on this, in the Gulf Stream is a highly frequented region for commercial traffic. So how much would we get from the ocean side, just if more of these ships would have something?
Yeah, you know, using the turbines is a wonderful idea. It's just dealing with the flow distortion from those turbines is the difficult problem. People are certainly trying to characterize the ocean nearby those platforms, you know, predominantly with bottom-mounted ADCPs, for example, to look up and then have the data, you know, cabled straight into the turbine itself. You know, fishermen, you know, it's an issue. You have to be very sensitive to fishers, right? And the thing is that they find that these are really great places to fish quite often. They attract fish. So it's more a problem, I think, with the turbines than with the fishers. But that is, you know, we're very careful to keep lines of communication wide open with the user communities. And that's the best way to get, you know, environmental impact statements signed off. We're dealing with that right now, right? And I think BOEM is being smart by making sure that we have town halls, et cetera. This is what we're going to do. We actually have a fisherman who's not happy with us because we're putting moorings on the 600-meter isobath, and he claims that's where he fishes. So we're talking to him, and we'll see if we can come up with a compromise.
And I'll make one more comment. Since you're from Norway, about 10, 12 years ago, we instrumented Kvitebjorn platform, which is right off Bergen. It was a project with Statoil. And as part of the project, we put a wind LiDAR, a wind cube that is supposed to go up, and we actually pointed horizontal above the waves. And we realized that even in the best case scenario, when you're pointing the wind LiDAR into the wind, so the wind is coming from the right way, you experience flow distortion up to 100 to 150 meters away from the platform. And obviously, when you're in the wake, it's nothing, like no useful data. So the flow distortion, both in the water and in the air, is a huge challenge.
Hi, Luc. You did so many interesting things that lap over to the LES. It would take all afternoon to ask you questions. So we'll do that later. But I wanted to ask Samantha, can you disentangle the effects of the SST versus the gust? Maybe I didn't pose that quite right. Are the changes in the flux mostly due to the gust, or is it actually an SST effect?
Yes, I unfortunately didn't have an hour to present, but we have done a decomposition of using the data to look at the key anomalous components for both the latent and sensible heat fluxes. And we actually found there was a larger contribution in the sensible heat fluxes from the air-sea temperature gradient with the background wind acting on the anomalous air-sea temperature gradient due to the cold pool, whereas for the latent heat fluxes, the air-sea humidity gradient was quite small, the anomalous component, and thus it was the anomalous wind speed acting on the background moisture gradient that really seemed to be the largest contributing part. And so to me, that suggests that there is not so much a competition of thermodynamic and dynamic forcing, but more so a summation of the two, depending on the heat flux, if that makes sense.
Great. So I have the mic, so I'm going to quickly ask a general question that I've been wondering about for a little while, and no one ever brings it up. But Samantha touched on it earlier when she was talking about the the instruments that leave a green footprint using, wind energy. I was wondering, I guess from a high level, is there much push to be more green in terms of our observational equipment?
I can start, I suppose. I feel that I work with NOAA, and I do think that there is an initiative to be more green. But even with the sail drone, we do see some drawbacks in things such as our navigational control and low wind, high ocean current regimes. And thus, we're considering looking at motorized options, like for just needing to cross features. But I do think that we should be aware of our green or our carbon footprint as we try to expand the amount of observations we have over the ocean.
Yeah, I was going to add one thing. So we're going more and more to these, uncrewed vehicles. And believe me, if you take a ship out for 6 months or whatever, you're going to generate a lot more crap in the ocean than you would even if you're running one of those diesel-powered platforms. Though you're not going to run those continuously, you're going to run them during field programs. So, getting away from ships in general is making oceanography greener. You can't do away with ships completely. Like I said, they still come in handy for a lot of reasons. But I think that's sort of why we are going in that direction, where you can collect the data in near real time in your lab, in your office, and you don't have to go to sea. So that's my take.
So I have a question to Joseph. Very impressive presentation. I envy that you have the system at NRL that has that capability. So my question is, does prior knowledge of energy transfer from large scale to small scale affect your decision in the implementation of the multi-scale data assimilation? For example, if you know that the energy is going from large to small scale, yes, you do large scale first, improve the small scale. But if it's the inverse cascade, then is it still true that you do the large scale first and then do the small scale?
I have never even thought about that. That's an excellent question. I've always just only thought of the forward cascade, and I don't know what is I've seen some where there's a magic number of spatial scales where that boundary kind of bleeds, like at the submesoscale where you can have inverse and forward at the same time. But no, from a data simulation perspective, that's like way on the frontier in my opinion. And that's an excellent question.
Thought. Yeah.
Yeah, exactly. Thank you.
So we'll take our last question from Leah.
I guess another general question for everyone. And it started in our discussion group yesterday when Elizabeth Thompson said that one of the top priorities should be to identify the largest sources of error that is going to affect the interpretation of our analysis in the future. So I thought I'd take advantage of this expertise to hear what some of you had to say on that.
I don't know if I haven't thought of it in terms of error, but I think you've seen on a lot of these platforms, one thing that the goal of this workshop was look at momentum, heat, and mass. Mass could be CO2, but it's also mainly water vapor. And I think we are not focusing enough on getting good measurements for the moist processes, I think, from the observationalists. I'm not allowed to look at anyone in particular, but the moorings that we put out do not have measurements, fast response water vapor measurements, but they could be easily added so that we could be measuring, having time series of latent heat and sensible heat flux, which I think is something that we need. So I have found that, people have done WRF simulations, for example, over SST fronts in a dry atmosphere. And what's that all about? It's a marine boundary layer. It's moist. Include moisture, at least in your model, and that's something I think, we could work on the moisture physics in WRF and make sure that they're working properly. So I'm glad that you're nodding your head, but that's that does introduce error into numerical models. And so I think that's important for just in general. I would love to see people, someone said about adding instruments. So we welcome people to add instruments to our buoys. As long as we can accommodate them, we'll do it. Right. So water vapor is one that I think is really important.
To bounce on what you were saying, the characterizing errors from all those observations is a challenge because it's easy to characterize errors for an instrument in a lab, in a control settings, but things change completely when you put it on a platform, an observational platform. And there is, I'm mentioning ESMOD again, the way we've been trying to tackle that is by cross-validating observation across platforms. What does an airborne radar, like Doppler scat measure? What kind of currents? What does DOVVIS measures? How does it relate with in-situ observation? What do you measure from an ADCP on the wave gliders, that is slowly moving up and down with the waves, et cetera, et cetera. It's not, it sounds simple, but it's not. So,
Yeah.
and but the good news is that we're starting to look into this very, very actively because we have to.
Yeah. I think that plot you showed was fantastic.
Yeah.
Because if you just show the result from the LiDAR and nothing else,
people were asking me.
You go, what? And then compared to the ADCP, it's obvious that you're doing the right thing.
Well,
it's working.
But it goes back, is an ADCP the right reference?
Yeah, and just to clarify, what we were talking before is both characterizing the largest sources of error in our measurements, which I think you answered, Luc, but it was also characterizing the largest source of error in the things that we really want to understand and measure. So like, I think Jim bringing up moist physics, moist convection answers that part of the question. So it could go both ways. Or Leah brought up like, what are the biggest sources of sensitivity in our models? And so yeah, I just want to make sure that we came across those questions broadly too. Like what are the biggest sources of error when we're trying to predict mesoscale air-sea interaction or mesoscale frontal processes? So in addition to characterizing our instrument error.
Yeah.
Great. Well, thank you everyone for all of the discussion. Hopefully we can continue this later in our breakout group. So can we just thank all of the speakers again? So now we have a break and it leads into the poster session. So I encourage everyone to grab a coffee and head straight up to the posters. So we have plenty of time to see all of those. The poster session ends at 3:55, so in about an hour and a half, and we will go into the breakout sessions. I'm hoping Sam will put the names up on the screen. Great. So again, you'll see your name and a group. Make sure you pay attention if you're a lead and a note taker. And those breakout sessions will start at 3:55. Okay, great.